Okay, so we start the afternoon session with the first invited of the afternoon, Kees Snook from the University of Amsterdam, and he's full professor there at the university and also leads three independent AI labs, I would say, okay, like companies. And he has been a speaker in the past in our workshop already, and his work on multimodal learning is, I guess, well known in the community. So let's thank the speaker for coming and enjoy the talk.
All right. Thank you so much for the introduction, and thanks again for having me. Today I want to talk about the PhD thesis of Yunhua Zhang, who I had the pleasure to supervise. And the title of her thesis is Multimodal Learning Under Visually Challenging Conditions. But before we get there, let's first give you an historic overview of multimodal learning in the video context. This is one of the first data sets in activity recognition used for machine learning based video recognition. This is work done by Ivan Laptev when he was a PhD student at KTH together with Tony Lindeberg. And they created this data set where other PhD students were instructed to stand on a soccer field and do very simple activities like clapping and boxing like this. So very artificial and articulated, but this was the start of sort of like trying to recognize activities in video. You may even recognize some of the students in those videos who are now professors themselves. I'll leave that as an exercise for the audience. They were using STIP features at the time and support vector machines. Of course, now nobody knows what a support vector machine is, but this was sort of like early days. And boy, did we make progress. So this is a video from people at Facebook with the C3D features, if you still remember, so convolutional based backbones, and this was really classifying activities in short trimmed clips with excellent results. So for short trimmed clips, this essentially nailed it. Work from my team.
Got everything I need right here with me. I figure life's a gift, and I don't intend on wasting it. Got everything.
Group activities in sports like volleyball matches, also a topic heavily studied in this community. Combination of long-range relations between actors and their objects and the relationships between them. So also a topic done in video recognition. This is early prompting work, where given a sentence, we could recognize and segment an object in a video. Segmentation results is not particularly good, I would say, but it is interesting that it does trigger on the right dog, so does not trigger on the dogs in the backgrounds. This is work from ICCV, the last edition in Paris, unsupervised objects segmentation. It is actually quite impressive how much progress we have been making. When I started as a PhD student, it was sort of like unimaginable that we would get there, at least at this moment in time. Last paper I want to show, this is work done with Hazel Doughty, working not only on what can be recognized in video, but also how an action is being performed. So looking into the adverbs of activity recognition, so to say. So an action is done slowly or quickly, or sneezing is done instantly or messily, what have we. Then there is one common assumption that all these works have in common. And also at this conference, when you look at multimodal learning papers, everybody has the same assumption. And as you may guess, this is known as empirical risk minimization and the IID assumption. So all these works assume that we have a training and test condition that are very similar, right? So what we have learned during training, we are bound to see again also during testing. And this is a very nice assumption if your training and test sets are similar, because then deep learning and our favorite approaches can do really well. Yunhua questioned this assumption in her thesis, and she considers multimodal machine learning under visually challenging conditions, typically where the visual conditions at test time are very different or slightly different from the ones experienced during training. And what is the influence on the multimodal learning scheme, so to say. So here you see some typical examples of real-world visual conditions that you typically do not train for. She wrote a very nice thesis with 5 chapters. I'm going to highlight 3 of them in this talk, where we will consider robustness to domain shift, modality shift, and also resource shift, and I will highlight these one by one. So the first chapter is about robustness to domain shift. This is work that was published in CFPR 2022, so it's already a while back. Worked together with Hazel Doughty and Ling Xiao. And here we looked at activity recognition under domain shift. So here are some examples. So this is what is called scenery shift. There should be audio, but I don't hear much. This is another domain shift, camera viewpoint shift. So we have the same activity going on, but recorded from 2 different camera viewpoints. This is opening a drawer, right? So the activity is the same, but the pixel content is completely different. And here's another one that we defined ourselves. We call this actor shift. So the actors are eating. So the activity is the same. The actor is totally different. Now, the proposed solution that we explored with Yunhua is to really approach this problem from a multimodal learning perspective. So while the pixels change a lot for each of these 3 domain shifts, the audio is pretty constant. Right? So the audio is actually a pretty good invariant for this domain shift problem. And the audio can be used in 2 different ways. So the first one is to identify characteristic sound signals. So for example, the eating makes the same characteristic sound, although the audio looks very different. So that is one cue for the audio. And the other cue, how you can use the audio, is sometimes you don't know what the audio indicates in relationship to the activity of interest, but you do know that certain activities can be excluded because of the characteristics of the audio. So you can use it as sort of like as negative information, especially for activities that are silent by nature and don't have a characteristic audio, right? That's the... Now, she proposed an approach that we call audio balanced learning. So what you typically experience when you train on a training set and you move on to a independent test set is that the label distributions between these source and target sets are typically different. So if you over-optimize on a certain label distribution during training, you will fail at testing because simply the distributions change. So And here you see an example on the source domain where you have rare interactions and frequent interactions. And on the target domain, the frequent interaction is actually much more similar to the rare one, but it will simply not be recognized because it is underbalanced in your training set. Now, the solution here is quite simple. At training time, make sure that each class and type of interaction is accounted for equally. Then the other thing that we did is what we call absent activity learning. So here, the activity is pouring. Now, this sound of pouring may not be very characteristic to sort of like, if you recognize the sound, you would immediately say, oh, this is pouring, right? But what you can say based on this sound is that certain activities are very unlikely, like washing, closing, and opening. So this sound is not indicative for these activities. So you can scratch those. So you have less room for mistakes, so to say. These two are nicely combined in nice architecture with different losses to optimize it. You can find all the nitty-gritty details in the paper. I want to demonstrate here how it works. So if you would do the scenery shift experiment on Epic Kitchens, where you train on the one scenes and apply it on a different scene, so the kitchen scenery changes for different activities. If you would train your classifiers in a visual-only scenario, you would typically score in the top one accuracy of 48. Now, if you use our audio-balanced learning and compensate for the negative parts, it would improve the results to 50.7 top one accuracy. And this is only during training time. So you only use audio during training. At test time, you would only rely on vision information. So even if you use audio only in training, your visual classifier will also improve. So that was the surprising finding here. And if you also have audio information at test time, results are actually even better. Second column shows viewpoint shifts. So you go from third-person view to egocentric view. So here again, this audio adaptive learning is beneficial. Now let's look at some examples. So this is actor shift. And this is sleeping, and the algorithm successfully predicts it as such. Here are other examples. So listen to the sound. Opening door. So here you have three training examples in the source domain, and this is the test. So the actor has changed, but the activity sound has remained the same. Other cases are also nice to look into. So here the source domain is drinking. Oh, those don't have video, but I have for this one. So the duck is drinking, but the algorithm thinks it resembles more the sound of eating in this case. Here's another one. These are people running on a treadmill, and here we have dogs running, but it is confused by the event that happened at the end. So the dogs jump into the water, and the sound of the water sort of like confuses it for the activity swimming. So it is not perfect yet, but it shows that sound has actually a very strong invariant property that you can use for multimodal learning across domains. And it has a much better adaptation ability than visual-only solutions. So it is really advantageous to be multimodal from the start. Our approach benefits from audio more than alternative audiovisual fusion methods. So we also tried in the paper to see what do other audiovisual fusion methods bring to the table. But the fact that they could not sort of weigh the effect of the audio was hurting these approaches where we have a benefit. And we demonstrated that with this approach, we can generalize not only to new environments, but also to viewpoints, and even can replace the human actor with an animal and still recognize the activity well. All right, so then the second shift we consider is the robustness to modality shift. And this is work that appeared at last NeurIPS in a paper called Learning Unseen Modality Interaction. And here we question what we call the modality complete assumption. So when you have a multimodal learning problem and you have a training set and a test set, here you simply assume that the modalities that are available at training time are also similarly available at test time. And of course, in a real world multimodal practice with multiple sensors, this assumption is pretty strict, because sensors can fail or can become unavailable. So typically these algorithms would break when these assumptions are hurt. Others have also looked at this problem. So they have looked at robustness for modality incomplete data, where one or more modalities can be absent during inference, but it still assumes that all the modalities that you see at test time have also been seen at training time. So our goal is to recognize unseen modalities. Oh, sorry, the text is a little bit hard to read. So we are interested in recognizing unseen modality interactions. So here you can see that at training time, we have seen RGB and audio in one device and audio and optical flow in another device. We still see those modalities at test time, but we now also see the new combination of RGB and optical flow that was not considered during training time. Simple concatenation of these unimodal features cannot learn this cross-modal correspondence effectively when the modality complete data is unavailable. Then we want that the accumulation is agnostic to the order of the modality. So we want to be set invariant, so to say, right? So the fact that flow always comes after RGB should not play a role. And since all modalities come with their own feature space and dimensionalities, it is not so easy to combine them, right? It's very easy to conceive that one modality will dominate, and that is what you need to avoid. So our approach consists of two stages. So each of the modalities has their own modality encoder. We don't change this, but we have this feature projection stage, where the goal is that the dimensionality of each embedding is reduced, where we strive to have all modalities to have the embeddings reduced to the same size. And while we do this projection, we also make sure that the modalities are aligned, so that they are reduced to their sort of like semantic summary. And these are then coinciding. So this is the feature projection stage. Then the second stage is what we call dual branch prediction. So we have a supervised loss often for the task of interest, but it is very likely that some modalities are more informative than others, or more reliable than others. So to take this into account, we have this dual branch prediction approach, where in addition to the task supervision, we also have a pseudo label that indicates how reliable this particular modality should be. We performed evaluation on 3 types of problems. So we considered video classification on Epic Kitchen. We considered video retrieval with lots of modalities like objects, OCR, faces, speech, audio, what have we. And also robot state regression is in the paper, but not in the talk. We made separate splits for these problems because we explicitly want to have modalities at test time that were unseen training time, right? So the numbers I present are not comparable with previous numbers reported on these data sets. And for video classification, we use a SWIN-T transformer, a ResNet for the optical flow encoder, and AST for the audio recorder. And for the video retrieval work, we use the provided MUltimodal features that come with the paper, original paper. Here you see some results. So these are results for our modality incomplete setting. So we have at test time new modality combinations that we didn't see at training time. And if you do traditional late fusion, you would score 18.1 top 1 accuracy on Epic Kitchen. If you would apply state-of-the-art modality complete fusion method, like the one from Nagrani et al., it would actually hurt your performance because all of a sudden it doesn't know how to handle this unseen combination. If you follow a modality incomplete tactic, it is slightly better than the late fusion baseline, but also not super effective. And if you would go to our unseen modality interaction approach, you clearly have an edge with much better top 1 accuracy and much lower mean recall for video retrieval. We also did an ablation where we vary the amount of modalities at test time. And what we noticed is that our model can handle any input modality, so it doesn't matter how many modalities are there. It improves robustness for all combinations. We did notice that the more modalities are available, the bigger the game, because there is more opportunity for cross-fertilization, so to say. Then the key takeaways from this part is that we can effectively make predictions for unseen modality interactions by feature projection and pseudo supervision. So to take this reliability of the modalities into account. And our approach is suitable for classification, retrieval, and regression problems, and can handle a wide variety of modality combinations. Then the third chapter that I would like to discuss is shift in resources. And this is work that's presented at this conference, again with Yunhua and Hazel. And here we look into low resource computer vision challenges for foundation models. And the inspiration for this work comes from the field of NLP, like so many innovations in vision these days, because they were first with these large language models and now large foundation models. And a topic that has been studied for a while in the NLP community is low resource languages, right? So large language models are great for Mandarin, for English, for Spanish, but for poor resource countries like the Netherlands, these models are not so great. So we wondered, is there a low resource equivalent also in computer vision? And this problem has basically been ignored so far in our community. So we define the problem of low resource vision challenges for foundation models. And to give you an overview of this problem, we are very familiar with high resource problems, like think the ImageNet data set, right? So this is typically big data that you can easily find on the internet, rather coarse-grained categories that define these data sets. And it's typically a very general domain, consumer photos, what have we. Low resource is the opposite end of the spectrum. So there's typically very limited data available for low resource data. It tends to be very fine-grained, so very specialized topic with small differences between categories, and a very specialized domain that you cannot easily get your hands on. And we defined a benchmark with 3 types of data and challenges defined on low resource vision challenges. So the first one is circuit diagram classification. So if you had electrical engineering during your educational studies, you may recognize this problem. If not, then this is really hard. So the diagram on the left is the pictorial representation of a circuit, and this is a circuit diagram of an audio amplifier as it happens. So our goal then becomes to, given a circuit diagram, classify the circuit function. Here's another task that we defined, the task of historical map retrieval. So given an old map from, let's say, the 17th century of a city in Europe, can you find the equivalent map based on modern cartography? And the third one is mechanical drawing retrieval. So again, a very specialized domain where the goal is to retrieve a 3D view drawing from a 3D rendered image or vice versa. Now, I challenge you to find lots of images for these problems. We tried really hard to find many on the internet, and this is what we found after a serious effort. So this is in the order of hundreds of images per train set, validation set, and test set. So this is really low resource, much smaller than we are used to. It is also nice to write a paper actually on such a small data set, because your experiments go really fast. Now, okay, so this is all nice, but then we tested how well do present-day vision foundation models perform on these benchmarks, right? And we took 4 off-the-shelf models. So we took CLIP, SAM, BLIP, and ImageBind. So ImageBind is from a paper at CFPR last year, and turns out that all these models perform kind of poorly on these tasks. So if you look at the x-axis, the numbers are really close to typically 10% or less. And overall, ImageBind does the best. And some of these models are actually very poor. So a blip and SAM perform very poorly on these tasks. So that's good, because that means there is a lot of room for improvement. So we consider 3 challenges for low resource vision data. So the first one is data scarcity. So you don't have a lot of data, so it is really hard to learn something from such few samples. The second one is that the data is very fine-grained, so the categories are very close, so it is really hard to get to the essence and the nuances in your representation, again, given so few examples. And last but not least, is a very specialized domain, so you should need highly semantic cues to make the recognition. Now, our goal in the paper is to provide 3 simple baselines for this benchmark to demonstrate that existing foundation models can be adapted to this low resource scenario, and also to inspire the community to take up the challenge and come with much better alternatives for these baselines. So let me briefly highlight these 3 baselines to you. So the first one focuses on generating extra training data. The second one focuses on tokenization in the transformer architecture to have more room for fine-grained details. And the last one is to update the attention mechanism in transformers for specialized domains. So let me first talk about generating extra data. So the first thing we did, we took Stable Diffusion and we generated more of the same data, right? That is what probably everybody would do. And turns out that is not a very good idea, because what will happen is that your small amount of data will be expanded a little bit, but it will be so similar that you really start to overfit. So that is the big problem. This is what we call label preserving generation of extra data. So what we did is we also have what we call label breaking examples. So if you play around a little bit with the parameters of Stable Diffusion, you can generate images that look still sort of similar to the data you have, but you can no longer recognize the category. So here you see that for historic maps, it still looks like a map, but you cannot say what was the city that the map is from. But it doesn't matter that we lose the label, because we can generate images that are similar in this negative sense, and they become valuable examples for learning. So we combine both these label preserving images and the label breaking images for fine-tuning. Here you see some examples. So on the left, you see label preserving circuits for a FM transmitter. And on the right, I wouldn't say it is still an FM transmitter, but it is sort of still a circuit diagram. Baseline 2 is tokenization to allow for this fine-grained distinction. We have limited data, so we cannot train a tokenization layer from scratch. That is sort of like out of the question. So what can we do? So what we did is we have the linear projection kernel, and we divide this into subkernels. And each of these subkernels, we assign a weight. So then we add a few extra parameters for these subkernels, and those we can optimize with the limited amount of data that we have. So this allows to have some fine-tuned adaptation, so to say. So that's baseline number 2. And then we have baseline 3 is exploiting the attention mechanism. So what we do here, for each token, we crop its region in the global attention map, and we combine this with the overall multi-head self-attention. So to really sort of like overemphasize on characteristic details in the image that are indicative for the category or the map of interest. Now, in the paper, we show that each of these adapters improves low resource challenges a little bit. You can go over the details in the paper, not so important here. This is what I want to highlight. So here you see when you combine all these 3 baselines together, and you fine-tune then existing foundation models. So we did this for CLIP, for BLIP, for SAM, and for ImageBind. So the top bar is sort of like the default when you run these models out of the box. The blue bar is another adaptation method that is more like for general purpose, like high resource data. So not optimized for the challenges of low resource computer vision. And the last bar is our combination of baselines optimized for low resource setting. And that really has a very good effect. So this demonstrates that low resource challenges exist, and they require another type of solution than the common approaches that we take for high resource data. Here are some hard samples where we still fail. So what we notice is that we are still overfitting. So our predictions are still overconfident because we have so limited examples. So this is a problem. And when there is a key regions like the presence of a battery in an LED circuit, we tend to overemphasize on these key regions. So how to balance what information locally in the image, that is quite important for this challenge, and that is, I think, interesting for future work. The other thing that we noticed is that we are not only low resource, but within low resource, we are also very long-tailed. So when we looked at the historical maps, we found a few samples of very distinct styles that were also very rare in our small training set, like the historic map of Innsbruck in Austria. The style of this map was very particular. We didn't have many instances of those, and then recognition fails. So that is also a challenge left to address. So the three takeaways of this work are that low resource vision is a real problem that deserves more attention in our community. It has three clear challenges: so extremely limited data, fine-grained differences between images, and highly specialized domains. We have provided a benchmark that the community can use and improve upon. We have demonstrated that existing vision models struggle, and with three relatively simple interventions, adapters, we can sort of like make these models better for the low resource setting. And that already concludes my talk, and I would like to conclude with an encouragement. So learning to generalize for multimodal learning in space, time, and across modalities is really an open research challenge, and first ideas are appearing, but there's really a lot of room left for further improvement. So I would like to encourage you to keep on working on that. Thanks a lot for your attention.
Okay, Nico, please.
Right, so I want to ask for the last chapter, because these images in general, so these low resources, the one you show, they have a functionality to them, right? In the sense that the circuit just does something. The map, it's also has a little bit of extra information, not only that. So are you keeping this this information in mind? So just in the circuit, if I don't put the resistor there, then it's not an amplifier anymore. And so just generating something very, very similar, it doesn't mean that it's still an amplifier or something else. So it's not only just replicating the pixels, but it's also to keep the functionality. I think that would be interesting to
yeah, we haven't considered that. We do notice that many low resource scenarios are very specific and also often tied to an industrial area.
So you need some kind of domain knowledge in order to solve it really.
Yes, because I was not trained as an electrical engineer. I had a huge difficulty interpreting these diagrams myself, but Yunhua was very fluent in them. Yeah.
First task, have you tried to use just your modality?
I'm pretty sure that we tried this too, but that is much worse than vision only.
What's the constant for where you expect that to work?
Well, vision is very strong, and it is really the multimodal combination that helps. So by itself, audio cannot generalize strong enough. Yeah, too much confusion from other classes.
But for if you consider slightly long horizon video, where maybe more than one event is happening, can you hypothesize maybe like how you would extend that kind of approach?
Yeah, that's a good question. Indeed, I think all the data sets that we considered are trimmed, so relatively short. So we're focusing on single action. If we would do longer videos, I think you also need to have like temporal segmentation to identify what belongs where. But we didn't consider that in this work. It's much harder.
So some of the hypotheses might break down, right? Because the audio that is like consistent across two different actors, might not hold because another event might.
Yeah, we saw that in the negative example of the dogs, because they were running, but then at some point they jumped into the water and they were swimming, and then got confused. Yeah.
The first chapter. In that, did you guys study what is the weightage in certain actions? The audio plays like a higher role in determining.
Definitely.
What are the studies of the weightage?
I'm pretty sure we have some analysis and ablation indicating the effect of the fusion per category, but I didn't include that in the slide. I also don't remember it, to be honest, but I'm pretty sure it's in the paper or in the supplemental. It matters. That's what I recall. Yeah.
Considering to treat the multimodalities, do we use similar or same encoders, transformer base, or the core, or we treat it different modality piece by piece?
Different modalities, each with their own encoder, but we make them similar with the projection stage. So they keep their own modality and their own specifics, but we make it similar in the projection stage so that it becomes a common representation where it can be combined. You're welcome.
Quick one, right? Thank you for the information. And about this audio, right, and vision. Before with Dima, we discussed about the complementarity and the redundancy, right, of the dual modalities. Do you have any takeaways to tell us, about this, right? So, audio may be completing the information or be redundant of the information that you are getting. Is there any?
So in many of the problems that we work on in video or in vision, the data sets is constructed in such a way that the best role audio can play is complementary. So by design of the data set, you can only demonstrate, yeah, vision will do best and audio will add a few percent. But as soon as you break this assumption of having perfect vision condition at training and test, which we always assume, then the conclusions change. And then there is a reason we have multiple sensory information as humans, right? Else we would all be deaf and only have eyes if vision would be best. So all modalities play their role, and I think we can benefit from having more real-world, realistic data sets that capture multimodal data, also presumably other modalities.
That's why it's quite the clip paradigm is not really good for audio and video maybe. So, audio is more complementary, as you said, right? Instead of redundant, like language maybe with description.
Yeah, I don't know. I haven't looked into that aspect yet.
Any more questions? Okay, you have the very last question.
Yeah, so, for the project, about the incomplete modality during testing, in contrast to that, what if a new modality that is never seen before during model testing? So, could you please comment a scenario like that?
I think that is yet another variant, but then I would maybe opt for a test time adaptation type of approach, where you try to sort of like take the knowledge that you have and adapt it to the best possible knowledge for this totally unseen scenario.
Okay, I guess we have to move to the next session and can thank the speaker again.
Thank you.
Okay, so the first presenter is online. Cool.
Yeah. So, hello everyone. First, let me just confirm, like, is my screen visible and am I audible?
Yeah, audio is not great, but I guess this is what we have in the room. And
Have you tried to change English? Just let's try it again. Yeah.
no, the point is displaying on from that one. Yeah, we can try this.
Just a sec.
Yeah.
Okay, can you try to speak again?
Yeah. Hello. Is it clear now?
Try again.
Hello. Hello, everyone. Mic check. Is it clear?
I guess the audience cannot hear. Yes.
So we go back with
Yeah, we go
with
back.
all the settings.
Yeah, but it's just okay. You can start.
Okay. So, hello, everyone. My name is Bhiman. So today I will be presenting our work, but before that, I would like to apologize on behalf of both of us for not attending the event in person. So that being said, I present multimodal understanding of memes with fair explanations. So as evident from the title, our goal is to examine meme explanations generated by vision language models through the lens of fairness. So let's understand with an example here. So given a meme, when a visual language model is asked what the meme conveys, it generates an explanation based on its understanding of the meme poster. You can observe here that a group of people are identified as participating in a race instead of people running from fear of death from the rocket. Additionally, the word democracy in the meme has swayed the model thinking that rocket symbolizes unity instead of death. So this example clearly demonstrates bias in the generated explanation, and our goal is to identify the reason behind it. But why memes? Memes are unique combination of image and text, plus they are widely used metaphorically. All these characteristics and associated metadata make memes challenging to understand than regular images. So we aim to examine the fairness of generated explanations when explicitly presented this metadata. To achieve our goal, we collected various publicly available meme datasets. However, they lacked certain inputs required for our experimentation, as shown with gray gaps. To fill these gaps, we used OCR to extract the meme text and vision language models to generate their captions, later used to generate the explanations as well. This new enriched and unified dataset of memes is our first major contribution. We used Lava 1.5 and MiniGPT-4 vision language models with following categories of prompts where raw contains only meme poster, and as we proceed, we explicitly add more information like OCR, caption, and metadata. So moving to evaluation, we begin with automatic evaluation using off-the-shelf models like toxicity, profanity, and APIs like Google's Perspective API. The table shows the result for Perspective API. It can be observed that very few explanations are classified as toxic, and when OCR and captions are added, which is like when we move from raw to P2, the toxicity is increased. We also see an increase in toxicity when moving from Lava 1.5 to Mini GPT-4. But this was not our main goal. Our main goal was to tell what the story all these metrics are telling. Interestingly, we wanted to find whether they are telling the same story or not. So interestingly, they are not. And when we examined the correlation between this matrix, we observed very less correlation among them, evident from the darker shade of the first two rows or columns of the matrix shown in the right. So this finding is our second major contribution and raises concerns about their reliability. So now to find the reason, we performed manual evaluation. Looking into the previous example, we found out that because of common visual feature of people participating in a race has led to such misattribution. Additionally, since the word democracy is generally used in positive sentiment, here the deadly rocket is seen in a positive sense. So with this evaluation, we found out four broad reasons of bias, that is towards common visual feature, towards group entity or gendered, towards image then text, and towards sentiment associated with words. The table shows their spread across the datasets and prompts. These findings become our third major contribution. During our manual evaluation, we observed that vision language model may struggle to understand the text in the memes and generate biased explanations. However, by providing the correct text through OCR, we can mitigate the bias. As shown in the example, where earlier the explanations says US democracy is flawed, which is not what the meme poster is trying to convey. However, later with proper text provided, it got the explanation correct. Another finding is that if the caption generated is biased, like here, the model thinks that the human is holding a hammer. This biased caption later influences the explanation to be biased. So these findings add to our contribution and should be utilized in mitigating bias. Finally, I would like to conclude that with an aim to examine fairness in generated meme explanations, we found out that certain vision language models carry biases. Through our proposed unified dataset, we performed both automatic and manual evaluations and found different origins of bias. With this work, we want to encourage efforts toward development of fair and safe AI. Thank you, everyone. Feel free to contact us for any discussions. Thanks again. I'm now open for questions.
Any questions from the audience? No? Okay, so I wonder, I have a quick question. Do you evaluate some qualitatives in this work? So can you tell us maybe some takeaway that you noticed by looking at the actual results and just comparing it like manually?
Between the automatic and the manual ones?
Mm-hmm. Yeah.
Yeah, actually, we did. So if you see this table, so for the first three data sets, actually, when we are finding this, like these explanations are biased, we also checked whether automatic evaluations are saying them biased or not. And surprisingly, the automatic evaluations among the first three, none of them were classified as biased or toxic. So that was another thing which we found out. And with the below two, in the below two, we only took, so here we have told like 10 samples, and those 10 samples are actually all the 10 samples which the automatic evaluation metrics told that they are actually biased. They were classified as biased. But in our manual evaluation, we found like 6 and 3 were only actually like these are the numbers like to be biased. So yeah, so
Okay.
they were not telling the same story like in our manual, and they don't coincide with each other.
Yeah. Okay, thank you.
Yeah, welcome.
Any other questions? Okay, so let's thank the speaker again.
Yeah, thank you.
it's to pull up.
Right, nice. Good afternoon, everyone. Welcome to my presentation. I'm Zhijiang Hu, and you can call me Kevin. Today I'm going to talk about our recent work, the denoise vision language fusion, guided by visual cues for e-commerce product search. This is a collaborative work with Shasha, Ming, Arnab, and Doc when I was interning at Amazon. The multimodal fusion is a powerful tool to integrate information from different sources. And the successful training of such models heavily relies on the alignment quality of the data sets. In the e-commerce domain, such data sets are usually collected in an automatic fashion. And hence, without additional human annotation, the alignment quality is far from ideal. The sellers used to provide a very long title that optimized for text-based search that contains a lot of attributes cannot be revealed by the image. Look at this example. There are 23 words in the title, but only 3 of it you can directly see it from the image. In such cases, if we train a model with such kind of data set, it will be very challenging to let the model align the image with the entire data set. The words like the BPA or facillates are noisy to the model. And to quantitatively get a sense of how severe the discrepancy it is, we leverage the Blip2 model to compare the embedding similarity of each phrase to the image. And we can see that for those words that can be directly seen from the image has a significantly higher similarity than those cannot be seen. And this goes with our expectation and also indicates that the current e-commerce data set contains a lot of noisy, non-visual descriptive phrases. On the other hand, it's not very feasible to manually clean a very large e-commerce data set. So we're wondering, given such noisy image text pairs, how can we effectively align the vision and language? And inspired by the previous example, we are further wondering, can we just let the model to pay more attention or reduce its attention to this unaligned part? And in this work, we propose to leverage the token pruning, which is a method commonly used for efficient deep learning to mitigate the negative impact from those noisy tokens. Since we want to let the model adjust its attention, we work with attention directly. Here we are looking at a heat map of the cross attention in one of the outback models layer between the text tokens and image tokens. A brighter color indicates a higher similarity. And we can see that for some words, it's consistently have a higher similarity than the others. So if we take an average across all heads, we can get an average of language tokens importance score. And assuming that if we can have a threshold, we call it gamma, and we compare it with this threshold, we can have a pruning mask. Those tokens that has lower importance will be pruned. And the question is, how can we get this gamma? And our answer is we want to model it as a learnable parameter through a pruning loss. And more technical details can be found in our paper. And we evaluate our proposal method with a data set of over 700,000 products. And also we investigate the efficacy of our model in 2 stages. First is we want to see whether it can benefit fine-tuning an off-the-shelf model for the specific e-commerce visual retrieval task. And also we are wondering whether for the model already in the production that is not trained by our method, can our method also help it? And all the training are based on the same data. And let's look at the results. We can see that in both stages, our proposed method can benefit the model with some improvement in the recall, especially when we want to fine-tuning an off-the-shelf general purpose model for the e-commerce purpose. We can averagely have a 5% points gain in the retrieval. And this indicates that the data set is really noisy and our proposed method can serve the purpose. And we not only evaluate with like cross attention based above model, we also look into the late fuse model like the clip. And in conclusion, in this work, we formed the noisy image text pair issue as a token importance problem. And we proposed the multimodal learned token pruning method to effectively reduce the negative impact from non-visual noisy text tokens. And we conduct extensive experiments with multiple kinds of models and in different stages, and our method is proven to benefit the model with additional performance gains. That's all. Thank you.
Thank you for the nice presentation. Any questions from the audience? Okay. You have a question, sorry.
Yeah.
Thank you for the presentation.
Thank you.
Really curious about the data set that you're using of common products. When you're looking at it, what percentage of the terms that were in your descriptions were like marketing or non-accessible terms as opposed to actually descriptive terms?
That's a very good question. We don't have very quantitative analysis to those, but my experience is the ratio is around 3 to 7. So only 30% of the thing in the title is about the product, and the rest of it just for the marketing or for optimize the text-based search. Yeah, so that means we have roughly 70% of the non-relevant part. Yeah, no problem.
And have you noticed some difference in maybe in different categories? I don't know, some categories are more noisy than others.
Yeah, we do have some investigation in the part, and we found that especially in the daily life product that it tends to have more like noisy words, and for the very specialized like motor or automotive, like say for the cars, for the phones, those things are more specialized because people just search by the like tag. Yeah, yeah.
Oh, we have another feedback.
Yeah. That's also something we observed, and to be honest, we don't have a very good solution to it, and we compare like by looking at different ways, like say by only looking at CLS token or by looking at the average, and we found each of them have their pros and cons. So it's an open research question. Yeah.
I have a question about how you label your image. For example, if you do like the coin paper. How do you know that?
Oh yeah, so we that's a good question, and we don't have the label for it. We just basically trying to our task is for the visual retrieval. So in this way, we just put the image of different angle as our retrieval label, and here we are just trying to show in the title, basically we can tell it's what's relevant to the image, what's not, but we don't have a very quantitative say how correct the pruning it is. Yeah, in principle, yes, yeah.
Okay. So we have time to speak again.
All right, thank you.
So the last presentation of this session is on Monday. And the title of the words translating indoor panoramas and city streets.
Yeah. Hi, am I audible to the Zoom people?
Speak to my.
Okay, perfect. All right. Hi, everyone. This is Tanmoy. I am a third year PhD student at Northwestern University in computer science. So this work titled in detail towards translating Indoor panoramas into descriptions. That was done when I was a research intern last summer in Zero Group. So fortunately, my managers are here as well. So yeah, so the high-level overview of the problem is that we are looking into a new kind of situation where the input to a model, like we expect a model that will take a set of panorama images as input. Let's say for each floor, it will take an ordered set of panorama images, and we expect the model to generate a coherent description of the whole property or home, right? So to this end, there is like multiple kind of novel situations that we faced. First of all, that there is kind of no similar research that dealt with set of indoor panoramas to description related research. So to solve this thing, we came up with, so there is like no data set available. So we came up with a data set which facilitates this research. And this problem is highly practical because let's say like the real estate agents, that those people don't have to write anything if we have a model that actually does the job for them, right? And they can just do like slight modifications on top of the existing generated description of the home. So in short, our contribution first is ZinDetail dataset. So from Zillow, there is already a Zillow Indo dataset, if you know about that. So we extended the Zillow Indo dataset with language modality, and we call it ZinDetail. And the language that is present in the dataset is semi-automatically generated, and it is then human validated. And then based on this data set, we propose two benchmarks. So we propose benchmark on two objectives. First objective is basically evaluating the description generation. And the second one is based on the description language, can model retrieve the home or the floor plans? So to like get started with the research, we proposed a very kind of simple zero-shot baseline model named ZinD Agent. And after that, what we did is that we made some naive baselines and then compared the ZinD agent's performance based on those naive baselines on top of the ZinDetail dataset to establish like a benchmark for further research. So there are a couple like related datasets available. So the most close one is this one. I'm not sure. Sorry. Yeah. So the New York Sentences New York version 2 dataset, but this one. So in this data set, they have one panorama image with descriptions. There is no multiple panorama image per floor or per home that describes the property like in overall. So this is just like a room description. That's it. So there's like other work. I'm not going to the detail due to the time. So let me just briefly tell you the overall pipeline, the approach that we followed to generate the data set. You can see here. So what we do is that first, we have all the raw panorama images that is available in the ZinD dataset, also the floor plan image. Based on the raw panorama image, there are like annotations by the real humans of the room layout, window door opening vertices, and also like other information like room labels, transformations, and so on. So based on this and also the floor plan image data, we have the factual information, okay? And also, as we have the room exact locations of the panorama images, we can extract the connectivity graph between the floor plans, and combining this like factual information and the connectivity information, we built like a structured schema that is detailed in the paper, and that schema is being used in an LLM for prompting and then generating a description, which is kind of corresponds to the ground truth data that was annotated by the ZinD people. The people that annotated the ZinD dataset, right? So on top, you can see like a reconstructed floor plan where we have reconstructed the floor plan with the room-to-room connectivity and also opening connectivity between the rooms. And those are being used as a ground truth information for generating the description. So here's a sample description that you can see. And later this description is evaluated by people, real people, and then we calculate, we like extract the relevancy score and see if the description is relevant to the main property. Okay, so just to put a note, during the ground truth generation, ground truth data generation, we use both raw panorama images and the floor plan. However, we expect the model to generate the description only based on the panorama images, not the floor plan, because that acts as the ground truth, right? So yeah, so this is kind of like the UI that was used to check the relevance by the humans. So here are some insights of the dataset on the language endpoint, but this is the most interesting part that I want to share. So what we did is that we extracted the detailed dataset language descriptions and mapped them into map the embeddings of those descriptions into like 3D space, like using TSNA algorithm. And what we saw is that when two floor plans that are kind of similar, they share the same embedding space, whereas like the different kind of properties or homes or floor plans, they are projected into different embedding space. So that means we kind of found some interesting phenomena of like, can we like retrieve the home based on the description itself? Because we clearly seeing that this kind of thing we can do because similar kind of homes correspond to similar kind of descriptions, and so the embedding space, right? So this is the second objective that I was talking about initially. So to initiate the benchmark, we propose Zindy agent, which basically takes the raw panorama images, and it has four modules. One module does the room classification. Another one does the that does the layout estimation, and the third one does the depth estimation, and the fourth one extracts the room-to-room connectivity geometry based on only on the panorama images, and based on all the modules combination, we generate the predicted description, and then do the evaluations based on the predicted description and the ground truth description from the detailed data set, right? And on the bottom table, you can see the results where we have two objectives. The first one is language-based home retrieval, where we kind of compute the recall of the model to find out which floor plan or which home is the closest one based on the language. And we can see that the Zindy agent does better performance compared to the clip, nice clip. And same for the description evaluation, we use like foundation model Blip, and that our Zindy agent does better compared to the Blip 2 model in the sentence evaluation benchmarks. So there is like this is like the qualitative example where you can see that so for a whole property or home, there is like multiple floors, 3 floors, and for each floor there is like multiple panorama images. And here is the ground truth description. Here's the description that is generated by the naive baseline, Blip 2 in our scenario. And this one is generated by the Zindy agent. So in terms of several kind of matrices, you can see that Zindy agent does better, even in the qualitative scenario as well. Like you read the text on the sheet, you can, but feel free to read in the paper. Yeah, thank you.
Okay, there's a question from the audience. Maybe you can answer.
Yeah, that's a great question. So basically,
for those who can see,
you
can read it.
Yeah. So the question is how to quantify
How to quantify
the similarity between two floor plans. So basically, what we did here, that's a great question, first of all. So what we did here is that, let me just go there. So what's that? Yeah, for each home, okay. So this floor plan belongs to one home, like the property A, and this one is from property B. So we have the description from the properties, right? So then we map, like we extract the embedding space of the description and then map them into the 3D space. And that's how we kind of say that these two properties are semantically similar because the embedding space, projected embedding space is pretty close, like the points are pretty close to each other. Yeah.
Any follow-up question about that? No? Any other questions from the audience here? So just a quick one. How this model generalize in general, right? So if you can potentially apply it also for outdoor, right? Or is there any thing for like small pieces of the node?
That's a great question. That's a great question. For example, here for the Zindi agent baseline, sorry, why it's not coming. Yeah, for the Zindi agent baseline, so there is like a module named Salve. This is actually a paper from Zillow. Like it was also done by an intern in 2021. So what that guy did is that, so given some indoor panorama images, it tries to do like co-visible, it tries to create like a connection between multiple panorama images based on the co-visibility. So that one is probably difficult for the outdoor, but if this kind of model can be made for outdoor, definitely it's possible to generalize. Yeah.
Thank you.
Welcome.
So if we don't have any further question, we can thank speaker.
Thank you.
We have a short break now. We are coming back to the 3:40 with the next note speaker. It will be Laura Lab from Google. So we go for a coffee, we quickly get here now.
Sì, vi ho mandato il link. Ciao. L'avevo mandato già stamattina, ma non è arrivato nessuno. Quindi stamattina ti è arrivato. Perché l'ho rimandata.
Pomeriggio sì.
Scusami, sì,
Ce l'abbiamo rimandata.
l'ho mandata stamattina alle 8, ma poi non è arrivata. Ah, sì, a te è arrivata. Sei l'unico a cui è arrivata. Non è arrivato, sei privilegi.
No, in realtà sei 12:42.
No, infatti l'ho rimandata poi dopo pranzo perché non era arrivato nessuno. No, l'ho mandata a tutti, però si vede che ho chiuso la pagina prima che via. Quando le miei ci mettete i gesti, sto mandando in background, poi chiudo la pagina. Ora ho chiuso troppo presto e non ho ancora iniziato a mandare. Come al solito. No, ma anche lo speaker qua è perfetto. Lo speaker è dalle casse di quelle schifezze che racchiano.
We must this one because this one is a sort of amplifier. I mean, I heard the same.
No one is using this.
Here, it's not really.
I can actually try. I'm not sure. I have the drive. Yeah.
And the presentation, so we can leave Laura's face, so we can just passing by this Laura Negreta.
Yes, it's speaking. We have bottles. Okay. Camera is actually.
No, but now I'm sharing. Am I sharing the right thing also on Zoom? Perfect.
So you just arrived 2 days ago and tomorrow you fly back, right?
I arrived on Friday. Then we did some hiking around the area. Yeah. And there was the AC workshop, but I went hiking instead. But the plan was to attend, right? And then the workshops. And tomorrow, I mean, all the papers are on Thursday and Friday, so I will meet them. And we also have a demo, which I will
You have
show.
3 papers, right? Or more?
Two.
Okay.
Two papers.
Ah,
Yeah,
okay,
yeah,
okay.
yeah, yeah.
Good.
Yeah. And yeah,
So how big is your team now?
I mean, I still have students at T1. I would have 3 new PhDs at NVIDIA, and then I have like 4 full-timers, 2 more are joining, and then 1 million interns.
Okay.
So, yeah.
And do you have say a research lab at Firenze? So or are you?
Oh, no, it's remote.
It's all remote, right?
Yeah.
Okay. And you're used to this or?
It's better than I expected.
Okay.
So, yeah, I mean, most of my team is in Munich, so I can travel there and then, meet with everyone.
Okay. And how often are you in Munich now? You're still affiliated, right? Official?
Unofficially, let's say, yeah.
Okay.
Yeah. But yeah, maybe like 3-4 times a year. Go there.
Okay, that's not too often.
No, it's okay. It's also 1 hour flight, so it's fine.
Yeah, that's true. Munich is really very well connected.
Yeah.
I even fly here too via Munich, so.
Oh, really?
I know from Munich, Seattle.
Oh, okay, because people from Munich flew through Frankfurt or like, I don't get it. Okay.
Me neither.
This
So I got a direct flight from Munich to Seattle.
Okay, interesting.
And I met lots of people visiting CPI.
Yeah,
So.
maybe it was full, but they booked. I don't know.
Yeah, maybe, yeah. I think I immediately booked once the workshop got accepted because I had a small head start.
Yeah.
So I arranged hotels and lots of stuff.
Okay, yeah, then it was much
And
before.
then I had no issue with that. So maybe this is the reason. That's true.
Okay, yeah.
And I know that in Toronto, Sanya Fiedler, she's also, are you somehow connected?
Yeah,
to
we're
this
working
team?
together. Well, I mean, connected. We are, working a lot
But this
together.
is all one big family, so to say.
Not really, like, we are officially in different organizations, but it doesn't matter in practice.
Yes. There was the thing that this is split a little bit within NVIDIA, like having
The
daughter
research.
companies.
Oh, no, it's just a different organization inside NVIDIA, but
Oh,
it's
okay.
on NVIDIA.
Oh,
Yeah.
okay. Interesting. So how much compute resources do you have?
A bit. It's not crazy. It's not like, I think Meta has much more, for example.
Okay.
But it's still like allows us to do a lot of stuff.
So you're also diving into generative models.
A little bit,
or
yeah.
or deep dive.
Yeah.
And this whole Lotus stuff, is this more like a hobby for you, or do you, or do you give it up a little bit now, or do you think that is now explored enough?
No, it's more like expanding it a little bit, like what I'm gonna talk about today, like more expanding it to the open world segmentation, 4D, different modalities. So I think,
Okay, so this is something you, let's say, it's like a nice playground.
Yeah, it's like,
Interesting.
Yeah.
Yeah, well, you know that Roberto is now at Pixar.
Yeah.
I think, have you met your Cohn? Yes.
No.
It's a former student. He is now he defended, I think, 2 weeks ago.
Okay.
And now he's at Meta in London.
Oh, cool.
So, we quite have a few people now having finished and moving to very interesting companies. And it's very nice to see how you all developed over the last years. So such an amazing experience for me.
Yeah, I can imagine.
Yeah. And Yeah, I'm still very proud of your development all the last years. Just when I see your papers and some of your YouTube talks or whatever, just sometimes popping up for whatever reason. It's really nice to see.
Yeah, thanks. That's cool.
Yeah. Should we get started?
Yes.
Yeah. Made my homework. Not really. Oh, there it is. All right, so welcome back to our workshop, and it's my pleasure to introduce to you Laura Leal Pegé. She basically studied at the Technical University of Catalonia in Barcelona. Then she went to the Leibniz University of Hanover as a PhD student. She was basically one of my very first PhD students, helping me building up my lab in Hanover. And afterwards, she went to ETH, to Zurich, to Konrad Schindler in the domain of photogrammetry, and followed by a tenure track position at TU Munich, where she's still affiliated to. But in parallel, she's also working in Firenze and Florence for NVIDIA, and she's well known for works on multi-object tracking, autonomous driving, also more towards 3D tracking, generative models. And she received several awards over the last years. And I think one of the most recent and important one was the ERC Starting Grant in 2022, one of the most competitive grant schemes we have in Europe. And yeah, Laura, it's a pleasure to have you here. We're looking forward to your presentation.
Yeah, thank you. Yeah, thanks for the very kind introduction. So I'm really super excited to be here and to talk about a project that is deep in the heart of our research team at NVIDIA. So I'm going to talk about open world segmentation and tracking. And for this workshop, I decided to focus a lot on LiDAR representations and distilling information from 2D to the LiDAR sensor. So let's get started a little bit with the motivation and the research that we're doing in the team. So we're working towards embodied autonomous agents, right? We're interested in autonomous driving, robotics. And for this, like there are several places where perception could be very helpful. For example, providing the ability to the autonomous agent to understand what is around them, to understand the surroundings, to understand the dynamics. So how do agents around the autonomous agents actually move? Can I predict their trajectories? And also essentially to predict where the autonomous agent is, right? So for localization. So for this talk, I'm going to focus more on understanding what is around the autonomous agent and how do these agents actually move. So this is essentially a task that we can maybe call globally dynamic scene understanding. And I'm going to start with a little bit the reasoning on, different tasks that dynamic scene understanding encompasses, and also different levels of granularity in terms of how many classes can we actually handle for each of the tasks. So let's start with the basic semantic segmentation, right? So this is kind of one of the first tasks in which you want to assign a semantic class to each pixel in your image. And this now is something that we know how to do definitely for a handful of classes, but even for thousands of classes, right? So we do have data sets that contain this information. We can train our network in a supervised way. And this works really, really well, as we have seen in the past years. A little bit harder task is panoptic segmentation, in which we not only want to find out the semantic class of the pixel, but we actually want to differentiate between different instances within a semantic class. And this is also a task that has been relatively well solved for, a handful of classes or even thousands of classes. Then we start getting into the realm of the temporal domain. So adding this component, the temporal component, in which we have to now do multiple object tracking, multiple object segmentation. And again, here for a handful of classes, we do have data sets that are well annotated, but I very well know that it's quite painful to annotate videos for multi-object tracking. So this is not something that really scales for thousands of classes. But these are not really the tasks that I want to talk to you about today, right? I want to go one step further, and I want to add another dimension. And so here I'm not going to talk about 2D or even about 3D. I'm going to talk about 4D panoptic segmentation, right? So I'm really interested into going into this 3D domain and adding the temporal component on top and being able to analyze this and to find out a handful of classes, thousands of classes, but like honestly, this talk is about going more into the direction of open world, right? So we should not be limited by the number of classes. We should really go ahead and say, can I actually label and segment anything that I find with my sensor? So in terms of how would we go about solving these problems, right? If we find ourselves dealing with semantic panoptic segmentation for, let's say, up to 1,000 classes, we'd be like, sure, let's get some data, let's annotate it, let's train it in a supervised way. If we want to do multi-object tracking, we would say, sure, let's get some more data, but it starts to get annoying because now we need to annotate, 100 very, very similar frames. And you do need that annotation in a really fine-grained way, also temporally. So it starts to get really, really tedious, right? But if we really want to solve 4D panoptic segmentation in the open world, like this is the realm where we actually want our methods to be working. This is the real world. This is not something where we can rely on data annotation alone, right? If we have to annotate LiDAR scans in a temporally consistent way for, open world, like this is something that is not scalable. So in this talk, I'm going to focus on a couple of works from the group on actually leveraging the data sets that we do have in the community, leveraging all those labels, and trying to generate a model that can pseudo-label my data for 4D panoptic segmentation, right? So this is the goal, let's say, is how to obtain these pseudo-labels in a meaningful way. And in particular, I'm going to focus on 3D LiDAR pseudo-labels, and I'm going to focus on a couple methodologies. One is I want to obtain pseudo-labels by looking at the appearance of the objects, and the other is by looking at the motion of the objects. So the first work that I'm going to talk about is going to be the segment anything in LiDAR that essentially aims at leveraging vision foundation models to do the task of panoptic segmentation in 3D. And the second work is going to be based on, let's say, the old motion clustering, but in the LiDAR domain, where we actually want to detect new objects, even new object types, by clustering point trajectories in the LiDAR space. So let's start with the first work. So what do I mean to segment anything in 3D? So we actually want to have a method that you can prompt via text, and you can say, for example, hey, Sal, can you segment trash cans and fire hydrants? So in this case, the trash cans are going to be shown in blue, and the one fire hydrant is here in orange. There's just one fire hydrant in this scene, but I'm going to run a demo later, and we can have a little bit more fun with the model. But essentially, this is what we want to get to, right? So how do we make this happen? So we proposed a method which is called Better Call Sal, which is basically a first step towards a LiDAR foundation model. And so here my goal is to have as input a LiDAR point cloud and a text prompt, and my model should give me a set of instances plus semantics. So this is the task of panoptic segmentation in the LiDAR domain. And I want to be able to segment and classify potentially any object, right? So really targeting this open worldness of the problem. So of course, like the question of, can I actually manually annotate all the data that I need to perform this task is not really something that we want to pursue. We rather say, look, there's such great models that are already working in 2D. Why not leveraging all of those? How can I transfer all the knowledge from 2D vision foundation models into the LiDAR domain? And the important thing is that I want to really transfer this knowledge, right? I don't want to depend on having an image at test time and having to run these vision foundation models on the image at test time. So at test time, I just want to run everything on my LiDAR point cloud. So this is an overview of the two of the key ingredients of SAL. One is the pseudo labeling and the other is the actual model. So we have as input an unlabeled set of camera and LiDAR point clouds, and these are nicely calibrated, and this is going to become important later on. Then we have what we call the pseudo label engine. So this is where we actually transfer all the information from the 2D foundation models to 3D labels directly in the LiDAR domain. And then we're going to distill this information by training a model on those pseudo labels. And this model is going to be able to do zero-shot segmentation via text prompting. Okay, so how does this model actually obtain instances and semantics? So just a brief overview of the architecture of the model. We have, your favorite backbone for LiDAR point clouds. And then we have this, by now kind of standard architecture. Your object queries are going to give masks as output with some objectness value. And this is going to directly give you the instances. And in order to obtain the semantics, we're going to rely on another foundation model, which is going to be CLIP. So you're going to basically have CLIP features that are going to analyze text prompts, and then the CLIP tokens coming from the LiDAR point clouds. And this is what is going to give you semantics to your LiDAR point clouds. So with this architecture, we can do what we call zero-shot classification in the sense that we can take, any free-form text and get the semantics out. Now, the question is, okay, how do we actually train such a segment anything model? Because here it seems like we do need to have a lot of ground truth in the LiDAR domain. And this is something that I specifically said we wanted to avoid. And this is where I think the interesting part of the method comes in. This is the pseudo label engine. So here I'm going to show is kind of a video depicting how the pseudo labeling works. So we have our camera rig at the top, and we have the LiDAR point cloud. These two need to be calibrated because what we're going to do is we're going to unproject the SAM mask. So again, leveraging a vision foundation model, we're going to unproject them to 3D. And this is going to create our instances. And then we're going to take CLIP. We're going to extract the embeddings that are coming from CLIP from the images. And these are the ones that we will attach basically to the instance mask in the LiDAR space. So one of the things that happen on some data sets is that we don't really have 360 coverage of the cameras for the entire point cloud. So as you can see here, like part of the point cloud is really not covered. So we cannot obtain any pseudo labels for that part. And we do have a way of creating some sort of Frankenstein training point cloud. So I don't want to give too much details here, but this is something that we actually found a problem. Like you cannot really train on this partially pseudo-labeled point cloud, and we have like ways of dealing with this in the paper. Now, I've just talked, or let's say I've just told you that we're going to unproject 2D mask into 3D. And this seems like an easy task, but we actually put quite a lot of effort into making this really work, right? So if you just take the SAM mask and unproject them to 3D, you're going to have all kinds of bleeding effects. You're going to have all kinds of errors because the 2D and the 3D don't really completely match, right? So what we actually proposed was to kind of combine the object notion of the 2D domain of the SAM mask with 3D clusters that we can obtain with DBScan directly on the LiDAR domain, right? So there's an overlap between these two clusters, the SAM clusters and the DBScan clusters, and this overlap is what we're really targeting, right? So again, there's tons of analysis in the paper, but this is just to say that this is not a simple unprojection. Like there needs to be some work there to make it happen. So, okay, once we obtain these pseudo labels, we could just stop here. We could say here, this is my output. The pseudo labels are my output, but this would have two problems, right? One is that you would rely on the images at test time, right? And the second one is that your results are still going to contain noise. Even if we put a lot of effort on DBScan and whatnot, your results are still going to contain noise. So what we propose is to actually train a model on these pseudo labels. And here I'm going to show why this is important, right? So here we have like some baselines, like some 2D baselines of SAM plus dbScan, several strategies on how to combine these two sources of information. But here I want you to focus on two lines. So in the orange row, we're going to show the results on the pseudo labels that we actually use for training our model SAL. So this is going to give us this PQ of 48.7, which is not really great because as soon as we actually train our model on the pseudo labels, this is the green row, we obtain much better results, right? Like 70.7. So this is the difference between simply running the pseudo labels and actually training a model on top that is able to filter out the noise and really learn much more from these pseudo labels. And the other result that I want to point to is the fact that we have at the top, the first three, or let's say 1, 2, 3, 4, 5 rows are with a semantic oracle, which means that we focus only on the segmentation problem and we take semantics from ground truth. While the bottom 4 rows are with semantics that coming from clip features. So the real system that we would actually deploy. And you can see here again, comparing the orange line with the green one, that we obtain like 70.7 with this semantic oracle, which is very, very close as the result that we get when we actually train on ground truth semantics, basically panoptic segmentation, which gives us a PQ of 71.8. So results are really, really close, right? While if we actually use the semantics that are coming from CLIP, the result goes down to 27.6. So basically what this means is that we're doing well with the segmentation problem, and where we're having the real issue here is in semantics, right? So pseudo labels work really well for the segmentation problem. For semantics, not quite, we're not quite there yet. And this is essentially mimicking exactly what is happening also in the image domain, right? So we're having exactly the same problems here. Okay, so here I'm just showing a video of results. This is not at all temporally consistent. This is just, taking frame by frame and showing all the semantic classes that we can find here. So you can see a variety of classes that we can work with, like there's cars, the traffic signs, people, so on and so forth. But I think the most fun is if I actually show you the demo and we can, play around a little bit with it. So let's see if this is running. Okay, so here's a demo that we built. The images are only for visualization purposes. So remember that at input, we have only the LiDAR point cloud and our method is only working on the LiDAR point cloud. So let's see, I'm going to try to find our favorite object, which is a fire hydrant. And you can see there a little bit tiny, but you can see one up here and you can see one down here. And maybe even more in the images, you can see like the fire hydrant being correctly segmented and also the second one here. We can then do, your most like common objects like cars, road. We can try also like storefront and, more like weird type of objects, trees, so on and so forth. We can also go for like maybe more like different types of vehicles. Like, for example, we have this kind of vehicle that is not really seen often, but that we can still segment and we can still obtain the semantics from the clip features. We have also, for example, like small objects like postbox. So this you can actually see here, or I don't know, trash can, which you can see here. And the cool thing is that, of course, like we're relying on LiDAR, right? So if we go into, for example, night sequences, where visually it's super hard to see what is happening and it's super hard to really detect these objects, we can still do like a really good job in the LiDAR domain, right? So cars are not really a problem. I don't know what else we can try, like curb. I don't know if anyone has prompts for me to just try.
Traffic signs.
Traffic signs. So there is one here, one on the back. They're not really visible in the image, so that's a problem. Because I mean, again, like the coverage is not 360, but I think other sequences maybe have better traffic signs or more visible traffic signs. Let's see. Yeah, here you start getting more of these. See on the back, there's a stop sign and all these poles. Oh yeah, here you can see it at the bottom. The stop sign here. Any more ideas? Cyclists. I don't know if we have any cyclists here. Do you see any cyclists? Okay. Okay, we don't have any cyclists here. Pedestrian. Oh, yeah, that happens. Yeah, the prompt engineering on this thing is crazy. So yeah, for example, person works a little bit better. So we have, for example, here on the left, like 2 persons being detected.
Mural?
Sorry?
I guess it wouldn't work on mural, would it, since that's only
Mural. Oh, but I mean, yeah, I don't think the LiDAR is so smart. I don't know if it even understands this word. So I was actually surprised when you type like storefront that you can actually get this. Yeah. So it works really well. It's true that the whole prompt engineering on this thing is a little bit crazy, but not surprisingly. The cool thing is that this is just gonna Okay. Okay. Do you think they can hear me?
Yeah, they should.
Okay. Okay, sorry about that. So, yeah, essentially we have, or I presented now a method that basically gets data in an easy, very scalable way, right? So we don't any annotations on the LiDAR domain. So we can really scale this up nicely, just get more data, pseudo label and retrain the model, right? So this is a very nice property of this model that it scales really well. But there's still, of course, like some instances that you're not going to recognize, right? And the question that we have next is if there is anything else we could do. And so we thought, okay, you know, from all the objects that we might be interested in, the moving ones are the most critical ones, right? For autonomous driving. So why not actually find a solution for those specific objects? So this is where I moved to the second work, which is essentially obtaining pseudo labels by looking at the motion, right? What we call what moves together belongs together. So the idea is that we're going to have a very small set of labeled LiDAR streams. So here we're not going for 0 labels, and we're not relying on vision foundation models, but we do rely on a small set of labeled data. And lots and lots and lots of unlabeled LiDAR streams. And what we want to do is we want to train an object detector, right? We want to train a detector, for example, for cars. And the question is, how can I train this detector and still leverage the unlabeled LiDAR streams? So we actually propose a method to generate pseudo labels based on motion cues, right? So we want to be able to analyze LiDAR trajectories, and we want to say, you know, what the trajectories that are moving in the same coherent motion are going to represent an object. And then I'm going to extract that object, I'm going to place a bounding box on it, and then I can train my model with these pseudo labels. So let's go step by step into the 3 parts. So in the first part, we have the pre-processing of the LiDAR point cloud and the trajectory generation. So we don't want to work with static point clouds, but we actually need point cloud trajectories in order to make sense of the motion of those objects, right? So this is the first step. Then we're going to have the clustering. This is, you know, our main technical contribution of the paper, which is going to cluster these trajectories. And once you have these clusters, you can then say, well, I'm going to put a bounding box on top of each cluster, which is going to be the pseudo label that I'm going to train my detector on. Now, this is just the pseudo label generation, and then we have the second step, right, which is the object detector training. So here we just, you know, apply our method to all the unlabeled data stream set that I talked about before. We take those pseudo labels and we train our favorite off-the-shelf detector. So in our experiments, we use point pillars, but of course, like this is, you can take your favorite detector and just train it on the pseudo labels. So let me focus a little bit on the technical part that is interesting here. I'm not going to go too much in detail, but Jen is going to present this paper at CVPR on Thursday. Yes, so go bother her and, you know, don't ask me the questions. But yeah, like overall, what we want to do is we want to propose to segment moving objects with graph neural networks. And I'm going to explain later why this is the way to go. It's of course based, it's a learning-based method, right? So that's why we need this tiny set of latent LiDAR streams. But the advantage is going to be that this is going to generalize much better than if you use, you know, any other clustering methods, like for example, BBScan. So what we actually propose to do is we say, you know, we're going to create a graph where the nodes are going to represent the point trajectories that I was talking about before, right? These LiDAR point trajectories. So you can imagine, for example, you have a car, you have about 20 LiDAR point trajectories, and each of them is represented by a node. And the edges are going to connect the trajectories that might belong to the same object, right? So you're going to have edges connected all these nodes. And essentially what you want to figure out is the connectivity of this graph. So for this, we're going to solve it with a message passing network.
in which essentially what is happening under the hood is that you have these message passing steps in which nodes and edges communicate. They basically share features so that, each node is aware of what is happening in the surroundings. And you can imagine that this is basically what gives the node a really good notion of how nearby points are actually moving, and can then make a decision to be connected to those nodes and form an object or not. So the third step is essentially going to be our loss, is essentially going to be the goal of classifying these edges into active or not. So an active edge means that the 2-point trajectories belong to the same object. An inactive edge means that they belong to different objects. Then we're going to have some, correlation clustering to make sure that we have all the constraints respected. And we're going to extract bounding boxes from all these clusters of point trajectories. And these are going to be then our pseudo labels. So, okay, let's see some of the main results just to get, an idea of what is happening here. So first of all, I want you to focus on the gap that we have between the purple line. This is essentially a method trained on ground truth detections, and the green line, which is our method. So if we look at the column, the one before the last one, the AP, we see that we still have quite a large gap, right? Around 57 compared to 89 when trained with ground truth. But it's already much, much better than prior state of the art, which was essentially a similar method, but using DB-scan as a clustering method. And the main bad thing about that method is that, if you have played around with DB-scan, it's super, super sensitive to the parameters that you actually use. And so it really doesn't generalize to different sequences. So for each sequence, you really have to find the optimal set of parameters for clustering. Well, we wanted to do a bit more of an extreme generalization. We wanted to say, can we actually train our GNN, for example, on Waymo, and then test it on, let's say, Argoverse 2, completely different sensor? What happens, right? Like, does our GNN really generalize? And you have to think that the GNN doesn't really care about detecting objects, just cares about putting point trajectories together or separate. And so this is a task that actually generalizes really well. And we found out that it doesn't not only work on Argoverse 2, but it also is able to detect objects that it has never seen before. Like, for example, here we have a couple of examples on trucks and buses, and these can still be detected even though you never saw them at train time. So here are some of the results that we have for cars on Waymo. And again, like, these results don't really need to be perfect, right? These are pseudo labels that you then train your model on. So again, a similar reasoning as what we did for SAL. If we have some noise on the pseudo labels, the model is going to take care of it. And here we have results on Argoverse 2. Again, the model has never seen this data at training time, and it actually generalizes quite well. Okay. So I just have 2 or 3 take-home messages from the talk. One is that pseudo labeling is really, really a powerful tool, and especially when you start to leverage strong 2D foundation models. And so what we try to do there is take these strong capabilities and bring them directly to 3D without having to collect the same amount of data, but in 3D. There's geometric and 3D motion views that still need to be very much explored. So this was just kind of a first exploration that we did, but there's so much more to do there. And finally, maybe kind of a, hopefully an inspiration for you to actually work on 3D tasks, which are actually reliant on 3D label data. And to really work in this direction, I think it's going to open up tons of possibilities. So with this, sorry for the technical problems, but if you have any questions, I'll be happy to answer them.
Yes, thanks for the nice talk. We have time for questions or remarks.
Thank you. I have a question about the first project you presented. So I might miss something here. So you said with the semantic oracle, you're able to get 70 something, and if it's just clip, it drops to 20 something. Then for the demo, like, I'm wondering which model that is?
Oh, no, the demo is with Clip, right? The demo is the
Demo
real,
with
yeah,
Clip
yeah,
was
yeah, for
open
sure.
domain
Yes.
calculator. Then, so that one is the one with the 20, something people.
Yeah, exactly.
I
Yeah.
see. So that works pretty nice to me. So I guess, that should be enough. Split, right? Like, I guess there's no need for additional training.
I mean-
Take up the gas.
I mean, I think it depends, right? So it depends. There's still quite a lot of noise in the output, right? There's still quite a lot of dependency on the text prompts. So it's not so clear cut when you actually, compare with an annotated data set with a closed set vocabulary, right? We also have an analysis, I didn't show it here, with let's say what we call super classes. And there you see that results are much better, right? So this really means that it depends on the actual prompting that you use, right?
Well, I guess it depends on, this constraint domain, like, for example, if you do car versus cars versus vehicles, like sometimes you'll get very different
Exactly.
outputs. So I guess it makes sense to, group things into superclass.
Exactly, yeah.
Thank you.
Yeah.
I would have also a question for the first work. So you've shown that it works really well on night scenes and even with videos very expensive sport ones. But there's certain things where I, as a human, would have a strong bias to textual information. For example, zebra crossings on the road.
Yeah.
Do you think your model is able to handle this at all, or do you need multi-model information?
No, I mean, of course, this was the first goal of saying, okay, how far can we get with LiDAR? The final goal is to have a multimodal model. Yeah. No, that's clear, right? I mean, zebra crossings or like mural, for example, this example, like there is no way the LiDAR just doesn't have that information, right? So this is where an image would come in and provide much more information. There is also the problem of the range in which the LiDAR sees, right? It doesn't see too far away in depth. So there you can only rely on the image, right? So there's multiple motivations for using multimodality for sure. Yeah.
Further questions?
I have a question. In my experience, when you train with pseudo labels, the model is actually overfitting a lot of that noise. But this doesn't seem to be the case here.
Yeah.
Do you have any insights?
I think it's because the noise is not always the same, right? So when there's really noise that has a pattern, then you're going to overfit to it. Here, our experience was that the noise was a kind of random, and then you don't have this problem, right? The model is able to filter it out. But this, of course, we only found out after we did the experiments, right? So it's not so easy to.
So there's no trick to avoid noise overfitting here. It's just plain plain training. Standard losses. Okay, because there are tricks you can use, and I was wondering if you put into place anything, but just plain training.
Yeah.
Okay.
Yeah. Yep.
I guess we're not as familiar with like the situations that self-driving cars could be put themselves into and LiDAR, et cetera. Do you see this as something that will be applied out of the box in the future? Or do you think it's a foundation? You said you're trying to get as far with only LiDAR. Like, what should we use from this going forward? Can it be used out of the box, or is this a foundation for further work on some domains?
So I mean, you can use it in two ways, right? Like, let's say foundation model for LiDAR can mean many things, but one of the things that it could mean is that even if you don't use LiDAR at test time in your car, right, and you only use images, you still want to train the models on the images with very, very accurate information, right? And sometimes you want to have this information in 3D, right? So for example, we're using a lot of this model for auto labeling, which we then don't use to train anymore on LiDAR, but we used to train it on image, right? And then we do kind of the opposite, like transferring the labels from 3D to 2D. So that's one way in which you could use this model, even if you don't have LiDAR at test time.
Okay, I guess there's a question online, and then we can move to the next session. And the question is, what frame is used as a reference to calculate movements and trajectory?
Oh, it's just like the first one, and then we take like 25 frames into the future.
Okay, so you take the frame of reference of the first frame.
Correct. Yeah.
And then move on. Okay. Okay.
All right. Any other very final question? Maybe a question from an old man. So when I was seeing your talk, I was thinking about classic words on motion segmentation, Markov random fields. So why is your model more powerful, or what are the similarities and dissimilarities?
I think it's the classic machine learning versus the old stuff. The model is much more general, right? So the fact that you can actually train on Waymo and just apply it on Argoverse and it works, this is pretty powerful. And I think like for all the other methods, you would just need to tweak the hyperparameters, and this is not just feasible in practice. So that's the main strength of, I would say, most machine learning methods.
I can read it. All right, then let's thank the speaker again.
Yeah. Okay, good. Yeah. Okay, so we move to the last paper session of this workshop, and it's vision and language tools. So yeah, if the next speaker, paper 5, can come here.
All right. We have the first speaker, which is
Okay.
online. Yeah.
Oh, he's online.
Yeah, he's
Right. Okay. So
yeah.
first speaker can share his screen and
Yeah. Yeah, I see. It's sharing.
okay.
Hello, can you see my screen?
Yes.
Okay. So hello everyone. I'm Ali Daboui from Shula, Carnegie Mellon University, and today I'm presenting our work titled Leveraging Generative Language Models for Weakly Supervised Sentence Component Analysis in Video Language Joint Learning. So here we will give an overview of the targeted tasks in this paper. In our work, we have tried to tackle some common difficulties of traditional video language models. In general, we observe that when we extract representations from text information, the model doesn't attend enough to each component in the sentence. For example, you can assume that we have like majority of the sentences, they have a subject, they have a verb, they have an adverb, adjective, things like that. We notice that during the training of the vision language models, the representations extracted from the text doesn't convey enough information for each component of this sentence. So the tasks that we are focused here are video and text jointly given as inputs. For the target task, here we focused on video moment retrieval. So video moment retrieval, the task is to locating specific segments in video that match with the text input. We also consider video text retrieval, which involves finding relevant text based on the input video and so on. So these are some of the common tasks that we basically evaluated in this work. However, the general idea can be applied to almost any type of video text tasks. So the challenges here is that, first of all, conventional models fail to attend to every part of the sentence properly. In the example shown here on the right, for the video moment retrieval task, it fails to emphasize the word shot and ultimately fails to retrieve the correct moments from the video. Similarly, in text-to-video retrieval, the conventional approach fails because it cannot attend again to a specific part of the sentence which are tied to the video. The reason behind these cases can be rooted back to the presence of noisy text labels in web crawl datasets, which are used to train these feature extractors. So to alleviate this problem, a few papers suggested using weak labels alongside the original ones while training for a downstream task. And weak labels here basically shows the role of each part of the sentence. For example, given a sentence, a cat gets a shot, we can label the sentence by explicitly specifying different components of the sentence, and then use those information to train a model which better attends to the adjective, the subject, the verb in the visual task. However, collecting these weak labels is very time consuming and could be very costly and cumbersome. So here in this work, we will talk about the contributions of, here we will talk about the contributions of our work, which is to mitigate the challenges we have already talked about. So our goal is to develop a model, a mechanism that can be applied to any type of visual text type of learning and improve the attention of the model to different components of the sentence. To address this, to achieve this, we first get the help of an LLM as a generative model. So we generate weak text labels by changing the specific parts of the sentence. For example, here the input sentence is as a cat gets a shot. We consider that as our anchor text. And by prompting LLMs, we generate negative sentences, which have some like negative and positive sentences, which have modified components. For example, one negative case could be a dog gets a shot. Another negative sample could be a cat gets a chocolate. So all these sentences, they are very similar to the original sentence or the anchor sentence. However, one of the major components of the sentence is changed using the LLM. One important thing is that this sentence modification and generating the negative samples is completely automated. So by prompt engineering, we basically developed a couple of prompts that given an input sentence can modify some part of that sentence and generate additional or negative samples for training the model. So then we propose a mechanism to utilize these generated samples into the training to improve the attendance of the model to different and specific parts of the sentence. So at the end, we also, like as a contribution, we show qualitative and quantitative results that this type of cheap sample augmentation for text data can improve the performance of visual text-based tasks such as moment retrieval and text retrieval. So here is an overview of the solution that we propose. In the general video text models, we usually have a text which is considered as, which is paired with the input sample, which could be a video or image or anything else. These two things are passed to a model, which is a transformer based on recent developments and techniques. And the model tries to combine these two samples together using a multimodal attention so that it can come up with a representation that connects the two modalities together. In our case, we propose to add additional pairs to this training. So using LLM, we generate different sentences, as I mentioned. One sentence is a positive sample, such as like the original sentence was a man is looking at a paper. So we can alter the voice, make it passive. A paper is being looked at by a man to generate another positive sample. And simultaneously, we generate negative samples. We change the adjective, we change the subject, and we come up with sentences like this. A man is looking at a dog, a man is tearing a paper. And then during the training of the model, we use these generated samples to perform contrastive learning on the output of the multimodal attention. So we use contrastive learning, we maximize the mutual information between the positive pairs using the contrastive learning criteria. So the model forces the positive pairs to be close to each other in the embedding and far from each other in the same embedding. So one important point here is that during this contrastive learning, the model learns that when the subject of the sentence is changed, the output of the multimodal attention should change as well. So if we have a video of a man working with, like looking at a paper, it should be different than a man looking at a dog or at a specific object or a different animal. So this is the main idea behind this work. Another contribution of the work is that instead of using simple contrastive loss in our approach, we have proposed a novel adaptive contrastive loss. To achieve this, we have decomposed the simple contrastive loss for a sample into k contrastive losses, each corresponding to a specific negative. So during our evaluation, we noticed that not all not all parts of the sentence results in the same negative samples for training. So based on the importance of each component in the sentence, we come up with a weight that reweights the contrastive training objective in order to obtain a better performance in training. Additionally, we have introduced an important estimation module, which I discussed, for each negative sample. A nice thing about this importance estimation, which is like using the training, is that during the test time, by generating the negative text queries, we can get some insight about the importance of each sentence component in the input video. For example, by changing the subject, we can compare that with the original sentence. And by getting the attention weights, we will know which component of the sentence is more important with respect to the video. Here is the attention mechanism for the work. Here is the solution overview for the model. The loss function that we developed to basically have two different types of contrastive learning. Here are some qualitative results of the model. So the task here is moment retrieval, and we observed that in the ground truth, like after training the model misses some important information regarding the object in the sentence. But after training the model, our model, like after using the augmented sample, negative text samples, our model is enabled to basically attend better to the specific components of the sentence in the input data. Here are also some quantitative results. Across different baselines, we've shown that our model achieves significant improvement, and even simple contrastive loss applied on the negative samples augmented in our approach can result in improvement of the performance in moment retrieval and video retrieval tasks. Thank you very much.
Okay, so we have time for a quick question from the audience. Kenny? Right. Okay, so I have a very quick question, so maybe you can comment a little bit on the okay, looks like you kind of rank the importance of the losses, right, based on the negative samples and this how, yeah, exactly. So you're basically weighting, right, based on the importance estimation module, the different losses coming from the different negatives. So how actually this incorporates the idea that you want hard negatives to be like actually easy negatives to be more important in the training, because usually when you do contrastive training, you would like to encourage easy negatives to come into place, because those are those negatives which are more similar to the
right. That's a very good question. So all the weights in this method here for reweighting the negative samples, they are being generated by an additional attention mechanism. And the objective for training that additional attention mechanism is to minimize the whole contrastive loss. One important thing is that all the attention values, they are normalized. So they act as probability values. So the basically the total probability of or total importance of the sentences or sentence components is fixed. However, the model learns during the training to assign higher importance to the sentence components that eventually can reduce the contrastive loss and can result in like harder negative or easier negative samples for the training. So all these things are being done adaptively during the training, having the main objective as the goal of the optimization.
Okay, thank you very much.
Thank you.
Right. And next speaker. We have paper number 18, for which I have a pre-recorded video to play, but if the speaker is online, I kindly ask you to step in.
Yes, sir. I'm all right.
Okay, cool. So you can share the screen and start your presentation anytime.
Yeah, am I audible and visible myself?
Yes.
Okay. So, I am Uncle. Let's start our inverse paper, which stands for Intelligent Visual Encoder for bridging the modalities in report generation. And so there are some key challenges. Mainly, we face three key challenges in this project. First, in medical imaging, in pixel level details such as color for X-ray images basically is unnecessary. But region intensity and other details are important. So inverse employ this by using self-supervised manner and joint embedding predictive architecture. 1 minute, sorry. So predictive architecture to efficiently train the encoder in self-supervised manner to obtain high-level semantic representation. And second one is hard to align two different modalities in a common space. In complex medical visual and textual data biases makes this task also more challenging. So inverse incorporate a lightweight transformer which is known as CMQFL layer, which stands for cross-modal qualification layer, which utilize the output from a frozen encoder and find the most text-grounded image embedding from this and bridge this modality gap. And third one is high computation resource to end-to-end training of a large-scale models. So to solve this, we employ two-step training approach. In first stage, we train the CMQFL layer to enhance the visual representation, and in this second stage, we fine-tune our decoder. So coming to them inverse framework. So mainly we have one target encoder which gives the image embedding, and this is projected through the input of the required input of the CMQFL layer, and from this CMQFL layer we get the text grounded image embedding, and this embedding is given to our decoder to generate the report. So basically work of this CMQFL layer is reduce the burden of the decoder, and it will also enhance some key features to generate better report. So we'll talk each part of this model in further slide. First, this is our training of our encoder, which our trained encoder is basically the architecture of IJPA, which and after the training of that model, we employ target encoder for the further process of our model. So in that model, we for the training of this IJPA model, we use NIH data 14 class dataset, and this to train the CMQFL layer, we employ three objective. First one is multimodal contrastive learning. So basically, main objective of this objective function is align image text level using contrastive similarity of positive and negative pairs to calculate this objective function, we calculate mainly image to text similarity and text to image similarity, and compare the calculate the loss function using the below equation. So basically, we evaluate similarity between each query output and the text class token and take the highest pairwise similarity as the image text similarity and calculate the whole loss or objective function using the below equation. Second objective is multimodality matching. Basically, it enhances the quality of pairs with hard negative binding. It uses bidirectional self attention mask for queries and text. This means uh, all the query tokens attend both text token uh, and the all the text token also both attend the query tokens and text tokens also. And this query embedding captures the multimodal information. Uh, and third objective function is mask language modeling. This is the main one of the most important loss function, objective function. So basically, this is the language modeling loss, mask language modeling loss. For this, we use causal self-potential mask. So it will, in this case, query tokens attend both query tokens and text token, but all the text token attend only the previous query tokens and the previous text tokens only. So after using these three objective function, we get some increasing the performance of the result, and this is the qualitative result. So model generated two model generated output and the some visualization of that model's intermediate layer and the each word plotting the attention map of each word. Um this is some quantitative result. We for this model we use three dataset. One is mimic CXR, second one is Indian University chest X-ray image, and third one is base dataset. And for seeing for the effect of CMQ failure, we see that after selecting the correct encoder and the CMQFLR, we our performance of this model is continuously increasing, and the objective is same for the objective function. When we have employed three loss function or objective function, we significantly improve the result. There are some conclusion. Firstly, we present a novel high-performing report generation model to significantly advance the alignment of text and corresponding visual features. By employing two-stage training approach, mainly focus the initial trained on the CMQFL layer and then fine-tune our decoder. And second one is model's ability to generate reports without recording any additional annotation like some bounding box or some external age requirement of the age and some criteria of the patient health, some smoking or not, this kind of annotation. This is external annotation. And third one is CMQFL layer, which is three objective function contributes create but high informative image embedding. So this is the main one of the main things. And we have one limitation also. So our model's decoder is patent on natural language, which lacks of medical specific knowledge. So we have to integrate a ALM which diversely trained on the medical image and caption dataset. So it will help the model to generate better contextually relevant reports. And these are some reference. And we also in future work we also include some sub medical LM include so that we can generate better reports. And thank you. Is there any questions?
Okay, thank you. Any question from the audience? Okay, so I'm sorry we have to go quicker on the last presentation of the session. And thank you very much again for the presentation.
So good day, everyone, and thanks for having me. So the title of this paper is IGEN, an adversarial approach for instruction generation in vision and language navigation. My name is Lorenzo Baraldi, and this is a joint work with my co-authors, Niati Rawal, Roberto Bigazzi, and Rita Cucchiara. So, yep. So we are talking about vision and language navigation, which for those of you that might not be aware about this task, it's basically the task of teaching an agent to navigate an environment, which is usually an indoor environment, by following natural language instructions. So basically what the agent is given is a 360-degree view of the current position that it has in the environment, plus an instruction in natural language, which basically asks the agent to navigate the space in a given manner. And then the task that he has to perform is basically to follow the instructions and navigate the environment accordingly. And the instructions might be something like take a right, going to pass through the kitchen to the hallway, rather than anything else that mentions objects that we have on the scene, directions, landmarks, colors, and etc. And what's peculiar is that the agent doesn't know the environment in advance. So it's basically spawned in the environment for the first time. He hasn't seen it, and still it has to tackle with it and try to follow the instruction. So what we do in this paper is, well, instead of developing another architecture for VLN and trying to make it working better, we take a slightly different approach, and we don't develop a new architecture. So we take an existing one, and instead we focus on the training data. So of course, annotating training data for such a task is kind of expensive, in the sense that you have to have paths in your environment, plus humans to annotate with the instruction, to provide the instruction. And what we try to do is to annotate trajectories manually. So obtaining trajectories given a 3D environment is kind of easy, because you just have to sample a reasonably good trajectory in the environment. And then what we do is to develop an algorithm which can label those trajectories automatically, so without the need of a human being annotating the trajectory. So that's the model that we have. It's basically an autoregressive decoder model, a GPT-like model, basically. It's actually a fine-tuning of GPT-2, so it's a model which has already been trained on language. It reasonably knows how the word is done and how it works. And what we do is to extend it to take visual inputs and to predict instructions for trajectories. So basically, the input of the model is going to be a sequence of images encoding the path that the agent is going to take, which are encoded via a visual encoder and then inserted as the inputs to this language model. In addition, we give it an awareness of the objects that are on the scene. So we are an object detector on each of those scenes, and then place them as an additional input to the model. And then the model is trained to be conditioned on this and to generate the corresponding instructions accordingly. What we also do is to add position embeddings, segment embeddings, taking somehow inspiration from BERT to distinguish whether the information is visual or textual, and to give the model a better awareness of this. And in addition to this, actually, instead of training the model in the classical autoregressive way, so with a cross-entropy loss, we do something a little bit more sophisticated, because we basically train this model in a GAN-like manner, in which you have a generator, which is the model that I just described. And you also have a discriminator, which is, in this case, again, a language model, which takes the scene, takes the generated instruction, and tries to tell whether it's fake or real, so whether it has been generated or whether it is actually an instruction from the from annotated by a human, so from the training set. So you train this again in a GAN-like manner with the two classical losses for any GAN. And then at the end, you obtain a generator which has seen how to annotate those sequences, and in principle can give us new training data to train our models. So of course, the question then is, will it work, and will it enhance the navigation capabilities of the model if we add data like this? And to answer, we basically employed 3 data sets. So this is room-to-room, Reverie, which are both already annotated. So we use them basically for training the generator. And then we have this HM3D dataset, which is very large and made of trajectories, which however are unlabeled. So basically what we do is to take those trajectories, run our model on them, generate the instructions, and then train a navigator on the generated instructions. And if this works, it means that the approach makes sense. So a few numbers on the quality of the instructions that we can generate with such a model. On the top part, you see basically we evaluated the generated instructions with the classical image description metrics. So for those of you that are familiar with captioning, GLEO, Meteor, Rouge, CIDR, and SPI, so all those metrics are basically going to tell you how much my generated instruction resembles the instructions that you have in the training set, so which are annotated by a human. And we compare basically without the GAN, without the detections, and we see that both of those things can actually increase the quality of the instructions. And also we compare and measure the diversity of the generated instructions. So, okay, we are capable of generating instructions which look reasonable, but how diverse they are we always generating the same thing or not? And with the adversarial training, actually, we observe that this diversity increases, which is actually a good thing, because it means that given different trajectories, I can actually tell different things, which is a good thing. And these are some of the samples. So you can generate instructions like walk into the bathroom with the sink and turn on the facade, or go to the office on level 1 and do the task. So given these sequences of images, basically you're capable of generating those instructions, which more or less look reasonable, and potentially we might be employed again as training data. The last thing that we try to do is actually the final proof. So train a navigator on this data and see what happens. So what we do is to take Duet, which is kind of a very famous approach for VLN. And instead of training on the regular data set, we also add our generated data to the training set and see what happens. And what happens is basically that most of the metrics actually improve with respect to the original Duet, and especially the success rate, this SR column, which basically tells you how many times have I been successful in reaching my target destination, improves, and especially with a lower length of the path that the agent has taken, which again is positive, because it means that the agent can go to the objective in a more straightforward way. This was on the Reverie dataset. We also did the same on the room-to-room dataset, which are somehow different descriptions. And more or less the considerations are the same, in the sense that, again, you improve the success rate and also you reduce the length of the path that you've taken. So that's it, more or less. So in conclusion, yeah, we developed a model to generate synthetic instructions for VLN and demonstrated that, yes, if you train on those generated instructions, actually you can increase your success rates and decrease the length of the path that the model takes, which is actually a good thing, because it means that generating synthetic instruction is a reasonable way of increasing the quality. So that's it. So of course, if there are any questions, happy to take it, and thank you.
The problem of, MUltimodal, they have hard time to understand left and right and stuff, right? If you ask, for example, go left, it's not working.
So yeah, well, this is, I mean, it's not really a foundation model in the sense that well, we start from a GPT-2, which is, I would say, language model more than a foundation model. But yeah, I mean, in this case, you have the sequence of the images. So actually distinguishing whether it's turning left or right is, I would say, easier. Even though I must mention that the encoding of each of those images is actually probably an open problem still. What we have done here is to use clip features. Yes, they are not super good into matching different things from different views, so that's an open issue. And yeah, probably one of the future possible works would be to have a better encoding of those images, which would actually also improve the thing that you are mentioning. Yeah. Thank you. Thanks again.
Thank you, Lorenzo.
Thank you.
So that concludes the last oral session, and we have now our last female speaker. You want to connect this to my Oh, I had one.
And I need to share screen.
Yes.
Okay.
Actually, if you don't have some, you can simply share the screen and speak through my microphone and without connecting the HDMI. Just share the screen.
Okay.
A little bit of
audio, yeah.
All right, so
Maybe
that.
That Paris, and she served as another chair to all visual conference. Now she is program chair for ECC 2024 in Milan. So participate. And what else? I mean, apart from what we are going to see today, she's working in many interesting fields like text to 3D and also sign language to text. So many interesting stuff. So give you the floor and thank you.
Thank you. Well, so happy to be here. The last, I guess, session, and also with the jet lag, so bear with me. So I'll be talking about a trilogy, so like series of three works we have recently worked on getting audio description in movies. So I'll just define what that is in a minute. But before that, a little advertisement of our group in Paris, where we like to take group pictures. So if you happen to be visiting the city, like just drop by, give a talk. Yeah, so it's active, a lot of people at CVPR now in computer vision. With that, so yeah, thanks already introducing some of my research. So here are a few examples of different things I'm working on. So they seem a little different, but to me, they're kind of the same tools, similar architectures these days, vision and language problems, but more to itemize the tasks. I gather them into like text to video retrieval for generic videos, but specifically for sign language videos to text. This is like one source of video where time actually matters compared to some other tasks, which is not necessarily the case.
And what I'm going to talk about today is like specific type of videos as movies, but that's kind of a nice test bed for testing long-term understanding, high-level understanding. So that's why, yeah, so it's important not just as an application, but also as a intellectually as for research. And yeah, the final one is text to 3D human motion generation, which is also getting a lot of momentum in the field. Like there were, I think, 4 workshops at CVPR, and I couldn't get in because there was a queue. But still, it's good to see more and more people working on this. So let's see if my, not here, I can hide this. I don't, okay, let's see if audio works, but I want you to first listen to a movie without seeing the pixels. So audio description is narration in movies that help visually impaired follow and enjoy the movies. So let's see just the movie alone and hope for the best. Where is this connected to?
Jonah? Hey, Jonah? Hey, Jonah?
Hi, Dad. This is Jessica.
Well, it's nice to meet you, Jessica.
Dad, this is amazing. If you play this backwards, it says Paul is dead.
Yeah, I know.
How do you know?
Goes on and on. But yeah, so you don't get to understand what's happening in the movie if you just listen to this audio, right? So it's normal. I mean, I don't know if you hear it from the back, but let's hear it once more with audio descriptions in between. So just also will help define what it is.
Jonah?
He goes upstairs and into Jonah's room.
Hey, Jonah? Hey, Jonah?
An egg-shaped chair turns round. Jonah's inside with a girl.
Hi, Dad. This is Jessica.
He has a portable record player.
Well, it's nice to meet you, Jessica.
Dad, this is amazing. If you play this backwards, it says Paul is dead.
All right, so let's now see the pixels that correspond to this. Hopefully you can hear. It's a movie from Sleepless in Seattle, as I was preparing the slides last night.
He goes upstairs and into Jonah's room.
Hey, Jonah? Hey, Jonah?
An egg-shaped chair turns round. Jonah's inside with a girl.
Hi, Dad. This is Jessica.
He has a portable record player.
Well, it's nice to meet you, Jessica.
Dad, this is amazing. If you play this backwards, it says Paul is dead.
All right, that was the last time. So I guess you get the idea. I mean, unless you were familiar already with what audio description is. It's a little different than captioning or dense captioning in videos because there is a goal. Like we want to describe things that are important for the story. There are guidelines on how to record audio generation. So it should describe changes, things that matter for the story, and emotions of the characters. So it's very important to so ground it to the characters. So it's not like the number of chairs or the colors of some jacket. So it's not like in captioning where you want to describe every single thing in the scene, but things that are important in the story. Yeah, so our objective is given a video of a movie, ideally as a function, and output this in the form of text. So for now, even if I show some audio, we are just outputting the text and then rely on text to speech. That's why it sounds like the airplane announcements, but there is some room for research on how to generate the audio, the sound in an engaging way also. Yeah, so that's what I said already. And obviously there is a societal impact on making more movies accessible to visually impaired. All right, in terms of kind of the input and output formulation, we have video frames as input, and I'm showing like a couple frames, but in practice it can go to 1 hour video. So it's not like a typical few second input task. And then we have a visual and language model that can also have multimodal input. It can have the subtitle, the speech as input, the context, so AD is audio description, the AD from the previous frames. So all this information we want to integrate into a single model that generates the caption. So before I go to this trilogy of Auto AD 1, 2, 3, I want to give a little background on like vision language models. I'm sure if you're here, you know quite a bit of it already. But basically, these days, what we are mostly doing is playing like Lego, bridging pre-trained visual encoders and pre-trained language models to find a mapping between them to tune to our task. And the language model, it can be GPT, it can be fine-tuned, frozen, visual encoder can be anything, convolutional, VIT, pre-trained, frozen. So these are like kind of decisions we make. And in terms of the bridge, it can be learning prompting. So the visual encoder is trying to generate prompt tokens in the space of language tokens. Or it could also have more interaction, as I will show a bit in a second, can have cross-attention architecture. So the first one, prompt tuning, is, so having this mapping network on the left to convert image into text space. So some popular examples of this is ClipCap or Blip2, for those who are familiar. And then it's kind of GPT-2 as if the previous text was this image, and then you learn to generate the caption of it. And then there's a number 2 version, which is the cross-attention, a bit like Flamingo style, where you have more interaction between the vision encoder and the text decoder, where there's this nth-gated cross-attention. So that's kind of initialized by 1, and then over training, it decides what to pass to fine-tune. And I'll show some results that if you have access to a pre-trained model of type 2, then it gets a better performance than just flat prompt tuning. But it's a matter of what kind of pre-trained model you have access to, because we don't have the resources to train these models typically. So in terms of training choices, you can have like discrete or soft tokens for the LLM. So it can be this mapping network can be a simple MLP, linear layer. It can be a transformer on its own. And you can train end-to-end everything or freeze some part of it. And in terms of the models that we pre-train on, typically, they are image encoders. And we need to work with video inputs. And what we do typically, so like just between this and this, means there are, instead of just a few patches per image, there is number of patches per frame, and then you just stack them all together. So you have the frame features. But what is typically done is to have some learnable vectors, some queries at the beginning that will kind of resample whatever the size of the video is. It will become a fixed size vector at the end of the training, which the visual tokens will go into as input to GPT. Okay, so that was kind of the background. And let me describe what we did initially as a first step to solve this task. At the time, there was GPT-2, I think, for this work, and a clip for visual features. And we were looking at how to combine the different multimodal data into a single model. And the first one is, a series of clip features. And just to say that the data we work with for movies, it's typically copyrighted, right? So you cannot just have access to pixels. What is done for some data sets is to release clip features or pre-extracted features, and then you build on top of that. So that's one of the reasons for this work. We didn't even have access to pixels. I'll show in the later work that we have also some efforts to get pixel data. The second one is subtitle context. So just like what we've heard at the beginning, there is a speech in between audio description. So basically, you need to hear, you can only hear one thing at a time. So there's either speech or audio description. In between dialogues, there's the narration that comes in. But whatever is outside the audio description is the subtitle, which is in the form of text. So it's nice for us because we don't have to have a mapping network. The same for the AD context. By AD context, I mean the previous, let's say I have like a series of ADs, and the previous generations give some context about what's happening. Ideally, it should also learn how to not repeat the same thing over and over again. If it says like Harry looks, the next time it should have a core reference like he looks, unless the word subject changes. So in general, like giving some of the context should help. And yeah, the last bit is GPT, which is frozen. So the mapping network that maps the series of clip features into visual tokens is, as I said, a series of frame features together with like fixed size learnable vectors. And then the AD context is the number of previous captions, not just the last one, but we take like the last 5. We do some ablation that 5 is a good number. And to differentiate different modalities, we have separation tokens that are learnable. So most of this, yeah, so it's a pretty straightforward architecture, but the challenge here is how to get data for this. So there's, to train such thing, you need complete movie data set where you have the video, features, subtitles, and AD. And there's this MAD movie audio description data set that came out in CVPR 22, where this is available, but it has 500 movies that corresponds to 300,000 AD captions, which is already a lot, but we've seen that this is not enough to fine-tune such large models. So just to give you an idea of what is available and how we can use them, there are lots of web videos out there that are typically very short. They are from a different domain than movies, but they have lots of like captions, so paired data of videos and captions, but they don't have AD, they don't have subtitles necessarily. Then you have the movies, which are, I mean, in theory, a lot of them, 3 hours of movies apparently produced every day, but of course we don't have access to all of that. But you don't have AD, the narrations for each of these. What you have for AD is like relatively small. So let me show you the actual picture numbers for this. So MAD is the one that has complete. It has the pixels, not the pixels, but the features, so visual features, caption like AD, and the subtitle. And we have a 300,000 captions for that corresponds to this. So what we did in this work is to collect text-only data, so just captions and subtitles by scraping a web page called Audio Vault. That gives us 3 million captions corresponding to a much more diverse set of movies, 8,000 movies, but we don't have pixels corresponding to those, so that's partial data. WebVid is one of those internet domain video text pairs, so just visual and caption, but they don't have subtitles. Conceptual captions is image and text, but no subtitles, doesn't have the video. So how can we combine all these data sets to train these large models? So yeah, the solution was to pre-train with partial data and then do a final fine-tuning pass with complete data. And yeah, so just before I show some results, let me give a bit more detail on this Audio Vault dataset, the text-only one, because that's an important source of a label that we'll reuse also in the last work. That's basically volunteers who upload narrations for many movies online. So it's not really necessarily professional audio, but there's no, and then people download the MP3s, the audio, and then plug it into their movies. So there's no movie associated to them. So what we do is we download these audio files and process it to have like a text, speech to text, ASR, with WhisperX, which is an extension to Whisper that includes diarization. So diarization is who speaks when, which is quite important for us because the narrator is kind of one of the speakers. We want to pick out what is the original movie dialogue and what is the narrator. And we have a few heuristics, like the narrator should never have first-person sentences. Like we kind of have a cluster of speakers, and the biggest cluster, and the narrator speaks a lot throughout the movie. So that's a big cluster, we know that. And that's a cluster that uses third person a lot, we know that. So we kind of find a speaker ID that corresponds to narrator. And then we have the time steps that correspond to the narration. So we get kind of AD automatically for 12,000 hours. So that's pretty substantial amount of data, except that we need to figure out which ones of these correspond to our movies. Right, so we train, as I said, with partial data, video and text part using internet caption data. The AD context part with text-only data from this 12,000 hours of data. And then we do a final fine-tuning pass with the MAD data, which is much smaller. So in terms of results, here is kind of the trend. The baseline is a single image per AD. So we assume that the AD segment, the timing is known. And if you only have one frame from this and generate the text, CIDR score is like pretty low. If you add visual context, so some frames around that, you get much better. And then AD context, meaning the last 5 text generations, you get extremely a big boost. And then the last 2 are kind of the effect of pre-training. Web-bit pre-training is not as effective as audio vault pre-training, perhaps because of the domain gap. One negative result that came out from this work, but I'm sure that it could be pushed, maybe revisited again, is the subtitles that did not help. Maybe there were too much information in the speech that was, the signal to noise ratio was too high. One thing we could do is to detect which of the subtitle elements can be relevant and then just give those. So kind of a filtering. Here are some qualitative results of Auto AD1. And I don't know if you know the Great Gatsby movie. The prediction is a man and a woman dance in a circle. So it's very video captioning like. It's not really like movie audio description like. As opposed to the ground truth, which is like it has the character names. Gatsby reclines on cushions as Nick and Daisy dance in the ballroom. No. Another example is from Harry Potter. His eyes widen. It's not incorrect, but it's a bit missing, let's say, compared to the ground truth, which is his mind fills with terrifying memories. All right, so from the first part, we've developed a prompt tuning, like multimodal approach, and we have kind of our first results for this new task. But one big limitation is that it's very anonymous, someone or a man and a woman, which, we know that is a bit useless for following a movie. And even, the text generations tend to be really short and incomplete, not very expressive. So in the next part in Auto AD2, we have looked at this character referencing a bit more in detail. And the question is whether we can give to GPT potential characters in this scene as an extra information so that it generates the names as well. And the way we do that is we want to provide their names, not just we don't want to just provide the character names in the movie, but also the actor or actress names from real life, in case Clip Features hopefully knows something about some of the famous people already. So how to achieve this? Well, we go to IMDb, so the movie database on an internet, where it comes with, for each movie, a cast of pictures and their names as a character name and an actor name. It's kind of an external knowledge base that we can assume is known when you produce a movie. And then we basically do a visual similarity between the IMDb image, so this portrait on the left of George Clooney, and cosine similarity across all of the frames of the movie, and find the top 5 highest similar ones to say these are the exemplars for this character. The reason we do that is that if you use the original image where the actor maybe ages over time or maybe has a different makeup for the movie, there's a domain gap between how they look in these photos on IMDb and the movie. So this is to reduce that domain gap. So we do that for all the characters to find a set of exemplars for each character. So we have, let's say, 5 characters for this movie. What we do is we have a character recognition module that is flexible. can take in any number of characters as queries, and takes the video features as input, and has a binary classification to say whether each of the characters is present or not in that particular scene. So at test time, you can plug in, so you can get the output of this to say, okay, the first two characters are present, and give that to GPT to say potentially present characters are, and then it solves the association with the caption, since we have this data to train with also. Yeah, so in practice, we have almost the same architecture as before. So clip features in, and then instead we have an extra prompt which says possible characters: Jack, played by George Clooney, the image feature Karen, blah, blah, blah. And yeah, so we expect the output to find, to also use these words. Another change we've done, as opposed to AutoAD 1, was to switch from this prompt tuning architecture to cross-attention version, as I showed in the beginning, like Flamingo style. And in terms of results, in a comparable setting, we have seen a big jump by using this architecture, so the cross-attention GPT. And in terms of qualitative results, it's much more
Concentrate,
So for this little clip, the AD segment, it says Snape points at Harry, Harry's eyes close in horror, as opposed to, I think at the beginning I showed, it was his eyes widen or something. So it starts to make much more sense. Another example is, yeah, one of my favorites, again from Harry Potter.
So how are we going to get to London?
We fly, of course.
It says like Harry rides on the horse's back as the horse goes up in the air. Yeah, so it's not really a horse for those who are familiar with Harry Potter, but still it's yeah, much more expressive, and surprising that it has all these character names right. So it's a bit cherry picked. It's not always getting the character names association right with the actual words, so it can mix up things. But yeah, it's better. And in terms of the limitations of AutoAD 2, well, we've got the character names in there, but still what is happening in the scene, the descriptions are not great. So especially because we are using pre-trained clip features, which might maybe for already lose some of the information, as opposed to using higher spatial resolution from each frame. And I haven't talked much about this, but I guess for people we've talked about this captioning metrics, for people who work on generating text and having a single ground truth that compares against these metrics like CIDR and BLEU, they are not necessarily indicative of the performance. There are like recent trends to have LLMs as a judge. So in this last AutoAD 3 part, I will show some of the efforts of coming up with new metrics to measure the progress. So yeah, improving the what, so what is happening in the scene. And the main, one of the main differences here is the change of going to a stronger vision and language model. So it's instead of clip and the GPT-2, we now switch to Video Llama, or the variants which use Llama as a language model in the first place. We have now a Q-former. So for those familiar with Blip, it's a visual encoder that has a higher spatial resolution. So instead of a single vector for the entire frame, it has multiple vectors. So to be precise, 32 per frame. And to apply such model, which is pre-trained, so it has already been trained on a video captioning data set. So it has even the bridge network. So this Q-former itself is a bridge network between the encoder and the decoder, is pre-trained already. So you can use it off the shelf as a captioning, which is our baseline. But except that it requires the pixels as inputs. You cannot just have some clip features on top. So we need pixels for this one. And once we have the pixels, let's assume we have, what we do is we train only this little tiny linear projection to fine tune it with the data we have, and have substantial improvements. So how to get this pixels data? So in ACCV 22, Max and like some of the colleagues, they have released the condensed movies dataset, CMD, where it's basically from YouTube, where the most important scenes from a movie is made public, so there's no copyright issue, but it's on the order of 10 scenes per movie, like each about 2 minutes, so like 20 minutes per movie instead of 1.5 hours. But at least they are like representative moments that are important for the story. And we have the pixels, more importantly, but we don't have AD for these. We have just the video and the sound of it. So remember, we have the audio vault that is only sound, and the CMD now has the pixels. So
Jonah, I'm home.
Here's the
Jonah, I'm home.
Okay.
He puts his keys and briefcase down and
it's a bit difficult to hear, but they're actually not the exact same audio. One is like from the webpage we crawl, the other one is from YouTube. We have to basically solve the problem of audio alignment between the one that comes from Audio Vault that has the AD in it, and between the one that comes from CMD that has only the movie sound in it. They are not perfectly aligned for a number of reasons, but more importantly, one has AD, one doesn't. So we do kind of an alignment to get to, yeah, so this plot is a representative one that shows the full movie on the x-axis that has maybe like 2 hours audio, and then the y-axis is the tiny 2-minute clip for which we're trying to find where it comes from the entire movie. Then we can transfer the AD. So they both have the audio in common, and we can create another data set, CMD-AD, we call it, for those that are intersecting by transferring the AD back to the pixels. So this way we've collected quite like drastically larger in terms of the diversity than the MAD that I showed earlier. So 1,300 movies for training, 500 hours of data, even if they are like shorter clips, because they come from a larger number of movies, they total to quite a lot of hours of data and a lot of AD. So this is made public, I believe. This is a release for at this conference, going to be presented on Thursday. Yeah, so the materials are being released and the code also for you to play. So that was the first source of pixels. The second source of pixels is a little bit funny one. How to 100 million, for those who are familiar with, comes from YouTube instructional videos where there's speech. So people are like showing how to perform some tasks. And this speech has been used traditionally for self-supervised learning, so learning common space between video and text. And more recently in this paper, How to Caption, they've shown that this speech, which is first person, can be turned into a caption-like text using some LLM. So it becomes, I am pouring, becomes he is pouring. And then we kind of assign fake names. In this case, it becomes John is pouring. And then we like pick a frame that is kind of the character profile picture. And we create a fake how to AD data set as a way of pre-training. Okay, so once we have all this data, so how to AD and CMD AD, we can train this video llama or video blip 2 to get same as before, getting the possible characters and this kind of stuff are the same, except the backbones are more stronger. And in terms of result, on this previous MAD eval test set, which is comparable for Auto AD 1 and 2, with Movie Llama, which is fine-tuned on CMD and How to AD, but has never seen a MAD training set, we have already a substantial boost. So that's one good outcome. But this was on the good old CIDR metric. And we started looking at things more qualitatively. One advantage of having access to these pixels, we can finally make qualitative results analysis. There you can see like the first row where you have ground truth, says the donkeys make a smoke. And then there's several predictions. In this case, donkeys use smoke, donkeys' children ride, where the CIDR score, even if they are similar, is decreasing over these different examples that have maybe not the exact same wording, but quite similar in meaning. And the same thing for Bleu, Meteor, and Rouge that are based on, text matching. And what we do in this work is to design a prompt that asks an LLM, can you evaluate the following movie audio description pair? This is the correct one, this is the predict one, out of a score of 5. And then it can be GPT 3.5 we used, or Llama, so that we found that they're correlated. And then it gives a score to say they're like out of 5, this one is correct as 4. And for these same examples I've shown earlier, we get 5, 5, 4, 4 that are also like correlated with the other metrics, but much higher and more interpretable, at least for me, than this values of CIDR. Okay, so that was metric number 1. Metric number 2 is, I haven't told you, but in the second work where we have character names, we didn't really evaluate how well we are referencing to the characters. So here we are introducing critic, co-referencing in text for identifying characters. It's basically just a kind of an intersection over union of how many of the characters and the ground truth we get right. So for that, there's a bit of trick to cluster each character into different ways of referencing to them. So it can be Jack, Mr. Dawson, Jack Dawson, maybe even like the name of their profession, so the doctor, or the relation, the father of. So all these things refer to the same person. So we just have a pre-processing to cluster them into characters. And then we just count how many times we get them right. So this is results on the new test set we've introduced from CMD-AD eval on the left, and MAD eval on the right, which is using the old metrics as before. So first thing to look at, I don't know if my cursor is working, is the first row, Video Blip 2 and Video Llama 2. These are two kind of pre-trained large models. They don't perform well off the shelf, so without fine-tuning on movies. So we need AD data to fine-tune these things. And then AutoAD 1 and 2, where we can compare against MAD eval. I've shown already the plot before. They perform worse, even if they are trained on MAD training split. So the last two rows are Movie Blip 2 and Movie Llama 2, basically the fine-tuning of the first two rows with our data, CMD-AD data and how to retraining. And we get a big boost. And the two architectures are quite similar. We just tried both to see if one is better than the other. But yeah, it seems with Movie Llama 2 is slightly better. And here are some final qualitative results.
Greg closes his eyes and folds his hands.
Oh, dear God.
Greg's eyes widen. Max looks at the candles.
Wish that one day Dad couldn't tell a lie.
The candles on the cake flicker and go out. The car is covered in smoke. The car is lowered into a pit. She runs down the steps and out onto the street. He lands on his back and rolls over. He turns to the crowd. The protesters run. The bunnies dance.
Okay. I don't know if you could hear them, by the way, from the back. It's all right. Yeah, so I mean, it's getting better. So this was 1, 2, 3, a series of works that occupied us for a year or two. But there are lots of future work, so it's a bit difficult to prioritize which one to do. So we're always like having a long brainstorming sessions. And here are a few like a future itemized list of things one can look at. So it's a good thing that there's plenty of open topics and in this research space where people have a bit depressing modes that everything is solved. It's not solved at all. There is like little coherence between one AD to the next, even if you have this context. So yeah, it's also computationally difficult to scale things to 1 hour. So we process things one at a time. So one can look at as a post-processing how to like clean this whole thing up to make it engaging, coherent to listen to, and to avoid hallucinations. So honestly, like when I look at some of these, it's full of hallucinations, but partially because we're using some language model that only picks up at a few visual features and then fills up the gaps. But there we can do like another round of grounding to check, maybe question answering to check, is this really the case? Do you see the horse here? And yeah, one way to do this is having a memory across the movie, because we have to save important places, important objects, and maybe movie-specific entities. And one way to get that is from external knowledge, such as plot summaries. So a lot of these movies, they come with like one paragraph of summary for the key events. And yeah, even if we call it audio description, we don't really either use the audio stream so much, so the musical, the sound effects, or we don't generate the audio itself. Yeah, so the last thing, which is I think a little bit more futuristic, is to have conversation. So for someone who wants to know more about the movie, can have an iteration of chat, so Q&A. And with that, I'd like to thank the co-authors who've done most of the work, and the data, as I said, for both AD only data, MAD, V2, I didn't talk about it, but we've kind of cleaned up V1, like the official version, which came from other colleagues as V2, and the CMD AD and how to AD are just released also. Can have any questions? Thank you.
Any questions? Yeah, please. You mentioned the issue of copyright with movies, right? But if you're doing a service for people who can't see the movies, they're blind.
Yeah.
Is that not possible to have a relationship with the movie companies to say, hey, we're doing this for the blind and therefore give us access?
Yeah, it's a good idea. I think they are doing it themselves. Like Netflix, we know, has some research, and Amazon as well. But yeah, I think one potential solution is to have partnership with them, but we know that it comes with a lot of overhead. So I think once we get to a point where we can start deploying things, we can get contact. But for now, yeah, I think we need a bit, like we need more steps to convince them that things are deployable in the near future, I guess.
Netflix and Amazon Prime are doing a great job today with 14 languages and so on.
Well, they're trying to hire our first authors. But to be seen. I don't have a good answer.
Yeah, thank you. Firstly, it's very great work.
Thanks.
And yeah, I mentioned how do you control the work velocity of your produced AD description?
How do I control?
Yeah, because I saw looks like the training data set is very verbose. You see that's a lot of details.
Yeah, the predictions are relatively short in the kind of subject, object, verb format, and that's one of the limitations. I think one has to find the right amount of detail. Also considering the gap. So one other thing I haven't mentioned is that we don't consider how long the AD should be and how much time we have to narrate it. So if you have only 2 seconds between 2 dialogues, you should just say very short things. But if you have like 10 seconds, you should keep talking. So I think that's another interesting area to look at, but we just do max cross entropy loss on the next like highest possible word, and it tends to output things that are pretty short. Yeah.
And hold on, another question. So
Oh, by the way, before I forget, I think we recently tried a more recent vision language model, which was better at captioning, and there we started having more expressive output. So maybe it's a matter of using better models.
It's very hard to define it for how much verbosity we want.
Yeah, so that's, I think, constrained by the time for us and the level of like the context. So if you've already said that we are in the Monica's living room in France, you don't have to say it again and again. So there's a bit of redundancy to be considered. Maybe you say it again in 5 minutes because the audience might have forgotten it. But yeah, so it's really, there are guidelines. Another thing we could do is to prompt the LLM with these guidelines. So describe if a new character came in the room. Describe if they are like looking at each other. So the relationships, emotions changes. And yeah, so scene changes. They move to a completely new location. You should mention it. So there are a few guidelines, but it should not be extra verbose either.
Yeah. So do you actually filter those, like the descriptions with some post-processing?
No.
So I think for the cinema, for this movie content, you don't have to be real time, so you can produce many descriptions.
Yeah, that's a good idea.
Yeah, I have another question, because I'm also working on the character identification. Do you think the current like IMDb data set is enough, to identify, have a good accuracy? I didn't see a accuracy measure.
We have some plots in the paper, but I mean, it's not perfect, especially it mixes up rare characters, like by picking up always on the main characters of the movie, which are appearing most often. But it's still pretty good. I think, I mean, recognizing faces these days is, I think, much better, like I can call it solved rather compared to captioning. So it's not too bad. I think the question is, what if you don't have the IMDb? How can you cluster and identify the characters?
Like the visual learning?
Yeah, with visual, you can maybe ask, are these the characters? And then just ask the user to name them. Or you can even propose names based on speech because they talk to each other, they mention each other's names. So that's also another interesting area. I mean, there are plenty of areas.
Thank you very much.
Thanks.
Yes, you already partially answered my question. First of all, thanks for this very nice talk. I really enjoyed it. So I was wondering, image capturing is very often very object-centric and even human-centric, and it's hard to capture the atmosphere, the context of the scene, the time of the day, and these things. So how is this reflected in your approach, and how much does it affect the, let's say, the experience of following the movie?
Yeah, I think that's partially why this fine-tuning helps so much between off-the-shelf application and this. I think for us, it's more the actions that matter, as opposed to, yeah, if there's a chair, we don't care, but we care if they're sitting down. But yeah, we don't have anything explicit rather than relying on the AD ground truth that has this kind of domain. Yeah, so what's the question? How do we evaluate? Yeah, I think there was one of the feedback we got for either 82 or 83, which was to have a user study. But we thought this is a bit at an embarrassing stage to present it to people. That's why we presented to an LLM. But yeah, I think at some point we need someone to rate how good these things are, especially for hallucinations. So to check how well grounded they are. But yeah, I think we're a bit far from having metrics for engagement. We're still like, this should be story relevant because as you said, we start from captioning models that are used to image captioning and short video captioning. And whenever they see a policeman, which is very common in movies, action movies, there is a police and then they start hallucinating the rest, like they're chasing someone. Or they see a hospital, they say they're in the waiting room, but there's actually like a action scene happening. There's like blood everywhere. But they just pick up on one word and then the rest they fill up. And that's partially because the captioning models refer to these a lot, I think. Yep, a lot to do.
Yeah, maybe just, I mean, first of all, thank you. And it's really nice to see how, a project, very hard project comes together at time, right? And keep pushing and see, how it enhance, the results and so on. So one thing is like, you mentioned at the beginning that you are having an arbitrarily long temporal window and you extract the features fixed size, right? How this impact? I mean, I mean, how the length of this sequence, how this impact in somehow in the
Yeah, I mean, we haven't done much work on, yeah, we have a fixed size. I think even Auto 81, we did some like number of frames of experiment, but I think we're still doing the dummiest thing possible, which is equally spaced frames over a given segment. And I don't think we've experimented with different architectures beyond the ones I've shown. So yeah. And especially when we're looking at some of these failure cases now, it can be easily, you can tell why the model makes mistake. And if you gave it another frame from like 2 seconds ago, it would resolve it.
Yeah.
But how do you know you should give that frame?
Yeah.
Like you have this shot between two people, like they're shooting, one is a gunman, one is someone like raising arms, and then because the camera keeps moving between the two, it thinks that the arms belong to the gunman, but I mean, it doesn't make sense. But if you give it the previous frame where you can see both of them at the same time, that's obvious.
Yeah, there are some progress.
Yeah, so I think how to sample frames is itself another question.
And about the metrics, right? You said,
Yes.
okay, caption metrics are good to a certain extent. Eventually, you have to use some like you use like GPT and so on. But GPT is really, let's say, good with marks, right? So I mean,
It's very generous.
It's very generous, right? So I mean, I would like to be evaluated when I was a student by GPT. So how? I mean, have you thought about, I don't know, giving some examples of, for example, grade 1 or grade 2, or just to let him use more grades? I don't know if that's a
We
problem.
tried it, but didn't make any difference as far as I remember. But yeah, that was one of the ideas, because for some of the movies, we have two versions, even English and American English, sorry, British and American English. And then we have paired data of things that should correspond. And then we have like an oracle to say, where like to calibrate what the score means. But yeah, giving examples from those, it didn't change.
Okay.
But Llama is more stingy with the grades. We have to tell it to be more generous to get it to the same scale. No, not Llama 2, but Llama 3 is more stingy. So I think it's not like off the shelf calibrated score across models either. But at least one thing is just nice with these is it's repeatable, it's reproducible. You don't need to rely on some users. Yeah, so pros and cons.
That's interesting to see that
Yeah.
different models.
Yeah, that's why this was kind of two models. I think we got asked in the rebuttal. But then after the paper was published, we tried another model and it was not, it was still correlated. They all go up at the same time, but the values are not calibrated. Yeah. For comparison between models, it's okay.
I don't know any other question from the audience.
All right.
Otherwise, we can call it a day.
I think my slides were stuck from the first slide on Zoom, but
Really?
apologies for that. Yeah, I see some chat messages. I didn't detect it from the beginning.
That's another new technical problem we have to go through.
Yeah, sorry for that.
Wanted this one. Right, take this one. All right, so we are now reaching the end of our workshop. Thanks for staying here to the very, very end. It was a long day, and yes, we were struggling with some technical issues, but still we managed. So would like to thank all the people who have contributed to the workshop here. So the participants, which are you. We would also like to thank the authors and the presenters, the reviewers who supported us in the review and the selection process. We had 5 great keynote speakers here from the beginning to the end. And so also big thanks to all the people who contributed here. And I would like to thank the sponsors not just the Computer Vision Foundation, also our home universities and other projects which supported us here with the workshop. So we hope we motivated you a little bit to continue with your research and PhD studies or whatever you're burning for. And yeah, we are looking forward to a great CVPR this year. Please enjoy it, have lots of discussion with other people, interact, do your networking. And then when you go home, I hope you are inspired for the next research steps you plan to do. And then who knows, maybe we meet next year for the next CVPR, maybe the 8th version of the MUltimodal workshop, maybe with a few slight modifications. But anyway, so enjoy the time here. Thanks, you stayed here all the time. And then, yeah, this workshop is now finished. Thanks.